Okay. Good morning, everyone. Thank you for attending this workshop today. And thank you for participating. Thank you for being here and for being part of this workshop. Next, our speaker, Robert, will we will talk about model selection with focus on decoupling, shrinkage, and selection. Welcome, Rob. Okay.
We're getting
the Wi-Fi. It's hard to get that out.
in honor of the Leafs first round series win. We've got something for Rob here. See if we can get this on the camera.
That's pretty nice. Thank you very much.
So the Maple Leafs Stanley Cup Championship jersey are going to be sent to Costa Rica.
That's pretty nice. I will wear that at pickup hockey in a couple days. Whoops. So Leafs had lost in the first round 6 years in a row. And if they had lost in the first round this year, they would have set the record for all professional sports for the most futile playoff experience of winning 7 years in a row. So they won in the first round, but then they lost in the second round. It was almost a sweep. So as a Leaf fan, we had about 4 days of feeling good about it. So
they lost to a very good team.
What?
They lost to a very good team. Do you think, Florida?
Well, they lost to the team that's in the final, but only gets you so far. So maybe a couple of things. I should have had a picture like this. In the examples, I didn't cherry pick it on purpose, but in the examples I showed you yesterday, the burn in with the sigma, it was like, oh, burned in right away. But I don't want to say BART always burns in immediately. So here's just another example. This is the beloved Boston housing data. So it's semi-real data. I don't know how real you want to call it, the Boston housing data now. But I'm just running BART. That's the MCMC draws a sigma. Okay, and this is a more, I should have had this picture. That's what I'm showing it to now, because initially, so at the top is the red line is the sigma from you would get from just running a multiple linear regression. And there's so many different ways to think about things. What's MCMC? Well, is this stationary Markov chain, blah, blah, blah. But maybe the heart of it is stochastic search. It's like coordinate, what's coordinate search and optimization? Well, fix everything, optimize one, then do the other one. And, give sampling is a stochastic version of that. So forget about all the Bayes stuff, blah, 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 blah. One of the miracles of modern life is stochastic optimization, right? It's just amazing. So just as a stochastic optimization, well, holy shit, it's pretty nice, right? So you just think of the estimate of sigma, the draw of sigma has how big your errors are. And you can just see the error drop, 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 drop. So it just is a stochastic search. So this example is just more dramatic in terms of the burn-in. So as a Markov chain Monte Carlo person, you go, oh, that's the burn in of the Markov chain. But as an optimizer, I just think, well, look at that optimization go. Yeah, and it's pretty darn nice. And again, it might be a fun session to go through how is BART different from boosting? In a big way, BART is different. Forget about all the Bayesian stuff, which I take very seriously. So I'm capable of taking it very seriously and completely forgetting about it in less than a second. So let's forget about all the Bayesian stuff and just say, the stochastic optimization in BART could be a nice alternative to the sequential approaches that you do in boosting. Okay, not to mention the dimension change and all other stuff like that. Okay, so there's some very nuts and bolts practical ways to think about how the BART algorithm could be a useful alternative to a standard boosting type algorithm. Okay, so that's just a better picture. The other thing as I went through yesterday that I thought was egregiously wrong, I had my list of like these basic theoretical things that would make you a Bayesian. So I don't know if the complete class theorem changes anything I ever do in practice, but I'm glad I know the complete class theorem. So everybody should look up the complete class theorem, just read it, right? And there is an interesting history there, right? Lots of these guys, the empirical Bayes people, oh, I want to get something that works, but I don't want to be a Bayesian. But I know if I want a good rule, I better act like I was a Bayesian. It's there's a long history like that, right? Why don't you? And then the other thing that so I was trying to remember things I left out. 3 things I left out. That, and then on my list of intellectual backgrounds, I left out just the likelihood principle. And that was egregious because I think for myself personally, that's how I first became a Bayesian. I read Birnbaum's 1950, blah, 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 proof of the likelihood principle, which is still a stunningly beautiful paper, where he takes these basic principles of inference that he feels like anybody would agree with, like sufficiency and conditionality, these 2 principles, and then proves that if you buy those, the idea being that I could get any frequentist to go, oh, yeah, that's right. Then there's a proof that you should obey the likelihood principle. That is, however, and it's a very abstract thing. It doesn't tell you what to do. It just says whatever you do, if 2 problems have the same likelihood, you should do the same thing. Okay. And that doesn't seem, and that has severe repercussions. There are, things like p-values do not obey the likelihood principle. So that's one fell swoop. P-values are logically ridiculous. That should be interesting to statisticians. Okay. So I left that one out. And then the picture that Samira mentioned should be in there too. And Rodney had kind of a version of it too, where you just show how, by adding up the trees, you can get partitions in an interesting way, as opposed to just building a big tree. Okay. Okay, so here's my webpage. And that's what I'll be doing next week. That was 2019. In 2019, the water was high, right? That's at 3,400 CFS, cubic feet per second. Usually the cubic feet per second would be more like 1,000. Now it's like 3. Usually when we go, it's like 500. Now it's like 3,000. It's a totally different thing. So our class 3 run is now class 4. This year, as you may have heard, the water is up. That's a big deal for America. Like Lake Mead is going up. It's a big deal for the West. But it's very personal for me because that's what I end up doing as opposed to a much easier run. But anyway, why am I there? Here's just my webpage. So here's all the talks. And I just want to mention, so the talk I gave yesterday is in our markdown, so the code, and the other talk I gave yesterday is in our markdown. So all the code is there. Not that there's a lot of code, but the topic I'm about to do now, there's a little R markdown tutorial there that I won't go through. I'm just telling you, if you're interested, there's an example there that you can work through. Okay. And if we do header BART, there's also, so the header BART topic, so it's very simple, what was BART for? Y equals f of x plus error, so f of x is the mean. Well, what about the variance? So we have a model that takes these ideas and does the mean and the variance. So this is actually a pretty nice vignette of the R package. And I went and looked, I noticed this vignette is not in the R package, which is a mistake. But if you actually wanted to use this R package, that's where you would go. And maybe just one more thing. So the talk that conceivably I might get around to giving in a few minutes, Rodney. So here's my webpage. So we were. the R package is right there, okay? So we didn't put it on crayon, but the R package is right there and how to install it. Okay, so if you wanted to try what I'm about to talk about, you would just install that R package right there. And oops. Then there's a little vignette right there. Okay. So I'm just going to go through this now. That's the actual, but I'm going to do it on this thing. So I have the Apple Pen. Okay. Okay. So model selection is always something people are interested in particular, variable selection. People really care about it. One of the things we try to do with modern machine learning statistics is say we get lots of variables, but then in practice, people always want to know, gee, I started with 100. Wouldn't it be great to know that out of 100, there's only 5 that matter? So in the talk I gave, wait, what day is today now? I'm getting confused. Tuesday, the talk I gave Tuesday, you're trying to predict stock returns, kind of a big problem. We threw everything in. So there's been 20, 30 years of financial people saying, gee, maybe this would be a good variable. So we just started with 62 variables and we got it down to about 5 out of the 62 that are really kick ass. So that's super interesting. That's the kind of thing that people want to find out. Again, why is the lasso better than ridge regression? If you try it on an application, I haven't seen too many applications where you actually get a kick-ass out of sample RMSE out of lasso better than you get out of ridge. I think that's worth knowing. So it's a little weird, right? People do love this fact that the lasso gives you the zeros. So maybe the point of my next talk is let's notice how ridiculous that is. Come on. If you fit ridge, you can just look and see which ones are close to 0 rather than having them exactly 0. That's a little interesting, right? Was that too strong? Anyway, but absolutely super cool is this idea. So the lasso and ridge, that would be in the context of linear models. And again, I think that document I started with yesterday where it's, okay, what do people actually use out there? And like I say, let me be totally cynical in a good way about this. Academics are useful. Most of the ideas that we really, do come out of academia, but I just love the fact that there's all these people out there just trying it. And I find that probably more reliable in the long run than whatever gets published in the short term. So people do try all this stuff. And the idea that you can do variable selection with machine learning models, I mean, this is so wonderful because, you start with a linear model and are the coefficients 0? Well, come on, it's not linear. It's just the whole thing started off wrong. But if you say to me, I'm going to fit a flexible model, and yesterday I argued when I say a flexible model as a practical matter, what do I mean? Either ensembles of trees or neural networks. There are other ones, but come on, those two cover what works. That's a big deal. So if I can say to you, well, you can fit one of these things and figure out what the important variables are, that is so cool. Okay, so that's a big deal. And then lots of these packages try to do it automatically, figure out what the variables are. So for example, trees have variable importance measures that have been used for many, many years. So I just found this quick statement in one paper by Friedman, which kind of summarizes that, but on the other, there's informally, they just go through a single tree and they go, okay, let's look at all the nodes, see which variables we're using the nodes, and then see how much using that variable improves the fit. So that in a single tree, I get a summary of, gee, how much work did each variable do? getting the fit. And then he's doing boosting, so he says, well, we can just sum that over all the trees, and that gives us a variable importance measure. So I use that. I got to admit, I use it. It's not bad, but it's also obviously logically flawed. In particular, how about this assertion? Anything that works by saying how important a variable is has to be wrong, because a basic insight you should have is a variable important? The answer is it depends what other variables are in the model. It's nonsensical. You're asking a question that makes absolutely no sense when you say is a variable important. So that rules out many methods. For example, the Shapley thing kind of works that way, right? So right away, that's very popular in machine learning. Rodney dissed it yesterday, I think, for computational reasons. I'm going to diss it for logical reasons. I'm going to say right off the top, it makes no sense. Bearing in mind that there's lots of things out there that make no sense that kind of work okay in practice. So for example, these tree importance measures, I just kind of argue that they make no sense, but they can actually work pretty well in practice. So, okay, so that's all the background. Okay, so in the next 5-10 minutes, I'm going to propose a way of looking for important variables in these kind of machine learning models that I think works better than these other things. It's not too complicated. I think anybody can understand it. And I've used it for quite a while, and it always works. And I think it's great. Okay. And for example, it has the property that there's no answer that says this is how important this one variable is. Okay, I just said that's wrong. This doesn't do that. It finds subsets of variables, and that seems fair. But it never says X7 is an important variable. It might say X7, X1, and X15 is an important subset, but it'll never say X7 is an important variable. So it's funny in statistics, right? We go these like decades with these methods out there that all these people are taught, which you would think that the first day any sensible person could say that's ridiculous. Why don't the students stand up halfway through the first lecture and go, you're supposed to be a professor. You're supposed to know what you're doing. Obviously, you've never tried it.
Will that affect their grade?
Well, I'll give them an A for that, but not everybody would. So that's a problem. So, how do we do model selection? So again, if you're a Bayesian, in principle, it's a gimme. You're supposed to just compute the posterior probability of the models. And that has an intellectual appeal along the lines of what I said yesterday. It's just simple probability. Yeah, I've got 3 models. What do I want to know? Given the data, what's the probability of model 1, model 2, model 3? But what's wrong there is this idea that there's these true models. Okay, is that the true model, or that the true model, or that the true model? Even that, I would say, is just kind of a quagmire. I don't need to believe. I'm going to argue it's not useful to believe that some of the coefficients are zeros and some aren't. You've ill-posed the problem from the very beginning. Okay, but nonetheless, there's a Bayesian approach to computing the posterior model probabilities. As usual, as a practical matter, even though it's not Bayesian, I often just use cross-validation. If you go into scikit-learn, which even if you're not a Python person, even if you're an R person or a C++, whatever kind of person you are, if you're here, you're interested in data science, it's really worth just going to the scikit-learn page and just looking to see what's there. That's a good exercise. So if you go to scikit-learn, so that's the mothership for Python, applied data science, machine learning in particular. So if you go to the section on model selection, so it's an interesting thing. You go to the scikit-learn, there's something on model selection. What the hell is that? So when you go there, it's going to be cross-validation. Okay. And I'm totally cool with that. How do you decide which model's better? Well, you see which one does better out of sample. So once you have a way of searching through a subset of models, then choosing amongst those models, you could do it by cross-validation. That's not a bad idea. So other than what I'm about to, I may get around to showing you if I actually give this talk, that would be what I would do in practice. It was me, and I am me. So often it is me. Okay, so I'm gonna make, here's my outrageous claims. I want something that's easy. It's hard, nobody will do it. I won't do it. I want something that, and this might be the fundamental simple thing I've been skirting around. I want something that starts from the idea of practical significance rather than statistical significance. Okay, so we all have statistical significance, but it's done in such a way that practical significance is lost. And if you understand everything, you can fudge it and get it right, maybe. But why build into it something where it's misleading to the casual user? Okay, so maybe we should stop and say, multiple regression is still a mother method that people use. You run a multiple regression in R and you get the T's and the P's and you get these stars. What human being is not going to think that the stars are telling them what the important variables are? Okay. It's not true. It's just not true. I don't see how you could possibly design software worse than that. Okay, so I want something that's easy to use, that actually works. I would like to be able to assess my uncertainty. That's kind of a statistical thing we like to do. And up till now, there's been nothing about BART, but that line is where I'm going to end up using BART for the reasons we discussed yesterday. I personally don't know another machine learning type method which at least approximately reports my uncertainty in a reasonably simple way other than BART. So if I want the uncertainty, which I don't have to get, but if I do want the uncertainty, which is a legitimate statistical idea, it was very interesting in the examples Rodney did yesterday when he was going through this thing. I mean, if you just looked at the fit, you would go, oh, the men are different from the women. But as soon as you added the uncertainty, you're like, maybe not. So in practice, it is important to get the uncertainty off that time. The last criterion is maybe one that you don't see listed too often. I want something that people could use without understanding this talk, without being as sophisticated as you are, and not screw up. Okay, so that's a little unusual, I would say, but why do I have that there? Because I just did a rant about how the standard software does not have that property. It has the property that if you don't understand everything, it's designed to mislead you. And that's a serious issue. So my outrageous claim is if you just do what I tell you, you'll be fine, even if you don't understand the damn talk. Okay, maybe I should skip this part. So I claim that we're motivated by a serious kind of decision-making utility background, but let me just skip to the actual algorithm. So, because it says right here, as often is the case, we cut lots of corners from the real thing. Okay, so let me start talking what the actual idea is. So I'm going to fit a machine. So for a while, I don't have to say whether I'm doing neural nets or doing BART, because I'm just going to use the fit initially. So I could get that out of a neural net at BART. But at a certain point, I'm going to have a method for assessing the uncertainty. And then at that point, obviously I'm going to use BART. I don't know what else I would do. So here's kind of the way this works intellectually, which I think is just different from lots of things start. So I fit some machine learner and I got E of Y given X. That's what you get, right? So what do I want to know? I want to find, so S is a subset of the variables. I want to find a subset of the variables such that a function which only uses that subset approximates E of Y given X well. Okay, so right off the top, it's totally different. So that the X on this side uses all the variables. Okay, because I'm saying, well, if I run BART with all the variables, it'll figure out which ones to use. And now I'm just trying to look at that BART function and say, geez, which ones does it actually use? That matter as a practical matter. Okay, so I view this as function approximation. I would like to approximate this function of 60 variables with a function of 5 variables such that the approximation is good. As a practical matter. How do I find those 5 variables in a quick, simple, easy way? Okay. So this only depends on the subset of variables in X. And E of Y given X is the expected value of Y given X in a Bayesian sense, but it could be just my neural net fit as well. Okay, so again, you could do this with lots of different learners, but every example I did do this with neural nets and it worked great. But usually, of course, I'm going to use BART. Again, if I want to do the uncertainty, I really need BART. Okay, so that's way too many words on the slide. I think I already covered this with my rants, my initial rants. What this says is if you go into the problem trying to look for testing the hypothesis that some of the coefficients are 0, things will not go well for you. I can remember as a graduate student, people saying, oh, as soon as your sample size is big, you always reject the coefficient is 0. It's completely useless. But if you go into the problem saying, gee, maybe a lot of the coefficients are close to 0 as a practical matter, you'll do fine. That's what you actually want to know. And if they are 0, you'll be fine too, right? Because 0 is close to 0. So get rid of the attitude that there's a truth that they're exactly 0. And I can remember arguing with Jim Berger about this. I'd say, come on, that's ridiculous. How often do you think they're exactly 0? And he would have some good example where it was plausible they're exactly 0. And I'm like, okay, there's one example of where the exactly 0 makes sense. But my point is, if I don't understand any of this, but my method is based on, I want to look for something that's close to 0, I'll be okay if they're exactly 0. But if I go into the thing looking for exactly 0, I'll screw up. Okay, so this is my idiot proof thing. If I take this attitude, then it's going to be idiot proof. And I'm perfectly willing to be the idiot. I need to be Rob proof. Okay, so now I'm going to actually just outline the approach, okay? Having promised a lot, so let's see if I can deliver. Okay, so step 1, I'm going to just run BART. Okay, so as we go through, again, sometimes it could be a neural net set of BART, but let's forget about all that. Let's just say it's BART, okay? So step 1, I just run BART on my data, on the training data. And, as we discussed yesterday, I don't know how MCMC draws. So D is the dth, little d here is the dth. MCMC draw. At every draw, I have a function. And every draw, I have the sigma. So that's the F hat we talked about yesterday. That's just averaging the rows of my Y hat test matrix in the WBART package. So done, okay? So step 1, learning from the data, you just run BART, get the mean, and you're done. Okay, so the rest is not, that's it for the inference, okay? That's it for the learning from the data. The rest is just trying to understand what we got. In particular, again, the goal is going to be, can I find, so this is going to give me a function of X, and I just want to see if I can approximate that function with a subset of the variables. Okay, so This step you may not have seen coming. I want to approximate the function, but I want to measure if I'm approximating the function, I have to say approximate the function where. That is, I want to specify at which x's I'm planning to use this function. Because the x's at which I'm planning to use the function, that's where I need to approximate it well. Okay. And I think there's a general idea there, which you say, is this model right or is this model wrong? Well, first of all, nothing's right or wrong. So you start off on a bad foot right away. But the answer to that question is it depends what you want to use it for. There's not even an absolute statement. Is this one wrong or right? I don't know. It depends. How do you want to use it? So this step, I think, is intellectually important because it says, how do I pick a good subset? First of all, you got to tell me how you're going to use it. Okay, and what does use it mean? Which x's were you planning to put into the function? That could affect which approximation I want to report to you. In course and practice, you might just use all the x's in your training data as a default. So that's a reasonable default. Okay. But I probably won't get to it at the rate I'm going. Rodney will stop me before we get to it. But I do have an example where it matters. Okay. And I think this is intellectually important. It should matter, right? It should matter. So I like that one. So if I talk about the Bayesian posterior model probabilities, that never comes up. Never comes up. Has to be wrong then, right? I like that. I always enjoy that. Simple principles that immediately make it clear that 90% of what everybody does is wrong. That's always fun. Okay, so I ran BART. And then I picked the x's that I want to do. Okay, so here's the actual search now. So we call this fit to fit. So this is the optimization I want to choose. So let S denote a subset of the variables. That's what I'm searching for, variable subsets. So remember, I'm not searching for variables. I'm searching for variable subsets. And so let the absolute value of S be the size of S, the number of variables, okay? So J is indexing the number of variables. So I could use one variable, two variables, three variables, so on. So for each J, I want to minimize over gamma S such that the size of S is J, just the difference between F hat. So F hat's what I got out of BART. And remember, BART was run without just looking with all the X's, right? There was no variable selection in BART. Now I could run Dart if I wanted to. I guess Rodney will talk about that later, which is kind of a variable selection-y version of BART, but I don't have to. And so gamma S is the function that only uses the subset S of variables. And again, I'm evaluating these two functions that have chosen. So the XF was the set of X's I chose. Okay. So again, having ranted about how, you should be different, you should choose these things. Obviously, the default is you put all the X's from your training data in. Okay. Okay. So that's just the squared norm. Just how different is gamma S from F. Okay. Okay, so I want to solve that optimization. Okay, so as often the case in life, if I actually tried to solve that optimization, I would go away and I would never come back. It's just too hard. So how do you solve optimization? Well, you make up a problem that's kind of like the one you want to solve that you can't solve. So in searching for subsets, I'm just going to use the backwards and forwards. In small problems, you can just try all possible subsets. But how do we do but given I'm doing backwards and forwards, what do I do? So how do I actually find the gamma S? So rather than, say I'm doing forwards. And how do I look for which variable works? So introduce one variable. How do you look for which variable works? Well, I don't want to run, if I have 100 variables, I don't want to run 100 BARTs. I don't want to run 100 neural nets. So this is the simple practical idea that I think makes this program effective in practice, is to get this gamma S for a given subset, we just fit a big tree to the data, which is F hat and X. Okay, so I just want a quick and dirty approximating function. And so that's what I need. For a given subset, I need a quick and dirty approximating function. And remember, I'm approximating the fitted function F hat. I'm not using the data anymore. So I just use a big tree to do it because that's, well-studied computational technology, works super fast. And that's the idea. So remember, why am I why do I say a big tree? Because I want a reasonable approximation to the function, and it could be in R64 or R10 or R20 or R200. And I want to get it fast and reliably. Okay. So this is a simple idea that can be tricky because, if I say I have data YX and I want to fit a big tree, well, as a statistician, lots of ideas come swarming over your mind. Oh, if I fit a big tree, I could overfit, and then I wouldn't do well out of sample. No. I'm not fitting data. I'm fitting the function. Okay. So big trees, where did big trees play a big role in modern data science? Random forest, right? That's what a random forest is. You fit a big tree, but then you fit, lots of big trees on bootstrap samples and average, and that fixes the problem of the tree being too big. So all that stuff you need to put aside. Remember, I'm not doing inference anymore. I have my F hat. I just want to approximate that F hat. I will assess my uncertainty by looking at the actual MCMC draws later on. But for my actual search, I'm just using F hat. Okay. So for example, let's just do, I think I just did this a second ago. Let's start running the code. What happens? You have P variables. You just go through, you just loop over the variables. For each variable, you create the data set, which is Y is the F hat with all the X's in at the X's you chose. And then you just choose the one variable, the J component. I'm looping over J. So the data I put into the thing to fit the big tree is the F hat. And my X is just the one X I'm trying now. And I fit a big tree, and that tells me almost very, very quickly, approximately, but the approximate, if there's one fundamental thing I'm claiming here that's not completely obvious, is that this approximation tends to be good enough to make the search effective. Okay. So then I fit the big tree. I fit the big tree with the data X1 and F hat. I fit the big tree with the data X2, F hat, ... XP, F hat. And that shows me, well, gee, if you just use X7, can you find a function that approximates the function of all the X as well? Okay, then I pick X7. Turns out to be the best. Oh, let's do it different. I picked X8. And then you just loop through all of the other ones besides X8 and consider introducing that X plus X8. That's forward search. So what's my first shot? I picked X8 the first time. I try adding in X2. Sorry, I try adding in X1. So I have X1, X8. I fit a big tree to the data F hat, X1, X. What did I choose? 7, right? Was it 8? 8. And then I just loop through everything but 8. And you just keep going. Okay. So that's where it's simple. Maybe I should change the way I give this talk because I have all these statistical ideas that I go through in the beginning. It might be smarter to give the talk like I was talking to some engineers who didn't know any statistics and just tell them, hey guys, I'm going to do this. I think they would buy it right away. They would go, oh, yeah, that's obviously not a terrible idea.
So we have a question online. So the question is, why do you want to approximate the predicted model, not the data with the subset models? Explaining the model. Why not explain the data? Is the model easier to explain?
So first of all, if I fit the big tree to the data, then all the statistical issues that I would be on the table. That's actually a hard problem. That's tricky. The fact that I'm not fitting the data, that I'm just doing function approximation is fundamental because that's what makes, I'm just going to use a big tree sensible. That's what I have to back up. That's why if I started with an engineer, they wouldn't ask that question because they wouldn't have all those ideas coming back with them. They go, oh, okay, that's fine. Yeah, I understand. You just approximate a function. So I'm deliberately getting rid of the statistical issues for a while. It's just function approximation.
So then when do you stop this?
Okay, so I could do forwards, I could do backwards, I could do all possible subsets. Okay. There is a step 3A here. It's after I've uncovered the subsets, however, if I do it, you don't have to, but often it does help a little bit to then go back to the data and run BART models, the actual data Y on the training X for those subsets. And that the F hat you get out of that as your posterior mean sometimes is a little better than the big tree approximation, but the big tree approximation is surprisingly good. Okay, so there is a thing in the R package that gives you the option of saying, okay, once you have the subsets, you can go through and loop over all the subsets and run BART just using that subset. Okay. But I don't want to use running BART every time I do my forward selection. First of all, that would take forever. And perhaps more subtly, and this gets back to the question, BART's not designed to fit a function. It's designed to do inference. It's designed to have the error. It's not engineered for the problem of function approximation. That's my basic idea. Gee, if I just fit a big tree, trees weren't designed for function approximation, but hey, if I fit a big tree, it works great, fast, a little crude, of course, but not so crude that it's not going to work. Okay, so I should probably go to the application right away, but let me, but as soon as I get to the, because that's important too. I will get to that. Okay, I will get to that, but let me get to, I'm just trying to decide if I can. Oh, let me try jumping ahead to the application and then coming back to where I need this rather than like too much. Let's get some data and all this stuff.
I have a naive question. I think I didn't get why fit is quicker than fit the whole data set.
I'm sorry?
Just why the fit is quicker than the data set, the original observed Y.
Oh, that's what I'm saying. Just fitting the big tree to that fit is much more stable, much more faster than actually running BART with all that MCMC. And running BART's a little tricky because, remember, I did go through, I had to pick a prior for that error variance, and that was intrinsic to the whole BART setup. What's my error variance now? In principle, I want 0. So there's a different engineering thing. If you just tried to run BART to do it, it wouldn't work as well. Okay, so let's look at the basic ideas I discussed in a concrete example. And maybe we could do it like I started here, right? Forget all that blather. So all that blather was for people who have a statistical background. So I have to disabuse you of these basic notions. If you knew nothing, I could almost start here, maybe. You'd be better off. Okay, so this is what I got this data set from Carlos Carvalho. This is like my links data, my Boston housing. I use it all the time. It's a really nice data set. So every observation corresponds to a used car. And the Y is the price that the used car sells for. So you're trying to predict how much a car will sell for. Totally straightforward application. You don't have to know anything. And then what are the X's? Characteristics of the car. So you measure characteristics of the car and you try to predict what the price will be. Okay. So most of the X's are pretty obvious, like the mileage on the car. So you might have the theory that the more mileage there was on the car, the lower the price. Okay. But in this simple version of the data set, we have 15 variables. Okay. And I have 1,000 observations. Okay. So let's not go through, let's not actually do a real application. If it was a real application, I'd go through all the variables and we talk about the variables. Okay. Let's make it a little bit real. Let's do this, a little bit of the sort of plotting you would do in a real thing. Let me mention one thing, because when I finally get to your answer to that question, something that's going to be important in a good way is you need to know what the hell you're doing. That is, I'm trying to predict the price. And when I first got this data from Carlos, I was like, Carlos, come on, it's a used car. The mean is 30,000. So these used cars are a certain kind of Mercedes. Okay, so you have to know something about the application. Yeah, that's a general principle, right? Any method that works without you knowing what Y and X is has to be wrong. See, that gets rid of the p-values right away, right? When you test the p coefficient equals 0, you don't have to know what Y and X are. So when I finally answer your question, I actually have to know what Y is. It's the price of the car. I have to have some sense of what the actual prices are like. Why do I have to know it? Because the practical significance is going to come up. I have to know what I'm talking about. I have to know the units of Y. Okay, so here's price versus mileage. So, okay, that's comforting. Maybe there's not a mistake. As the mileage goes up, the price goes down. Clearly nonlinear. Here's the price versus the year. So as the year goes up, the car is newer, so the price goes up. Okay. So those are box plots for the categorical variables. What's the price like in the different categories? In a real application where you would spend time looking at these. So that's the 3D plot of Y equals price versus the two X's, mileage and year. It's not a bad 3D plot as 3D plots go, right? You can kind of see what's going on. Okay, so step one, it's easy. You just run BART, BART XY, okay? And then after I run BART, I can use the predict method or put in the X. Remember I had X new or my very first application. So you put in the X's you want to predict it. Okay, but having ranted and raved about it, we'll just use the X's in the training data. So here's the actual Y values. Here's the BART fit. That's F hat at X from BART. Okay. So here's, I don't know how many BART examples we actually did yesterday. I have 15 variables. It's obviously nonlinear. I showed you the plot with 2 of them. I just run BART. Boom, it works. No problemo. Okay, so Y hat from BART. And then what I did is I fit a big tree to the BART fit using all the variables. Okay, so that's not what we're going to be doing, but just as an exercise, let's run the big tree. And there are some details to, I'm saying big tree. There is a little bit of detail of how big the big tree is, but they're minor details, I claim. So look at this. You know, it's a pretty damn good approximation. So that's supposed to make you feel better about the whole thing. And I'm just going to do that with subsets of the variables and find out which subset gives me a good fit to the fit, not to the data, not to the data. We're done with the data. We ran BART once, we're done. We're done with inference. It'll never come up again. And then just for fun, of course, there's the fits from a linear regression. Obviously crap. We knew it was crap just from our simple plots. The darn thing works, right? The BART thing works. It's a weird thing. Like why would you ever run out? Anyway. Okay. So I haven't done anything yet, but these are the basic, but it's not a bad graphic of some of the basic components that we've been talking about. Why? BART fit the fit with the big tree. Okay. So now we're going to do the forward stepwise, and then when do we stop and all that stuff. Okay. So this is just forward stepwise. So again, which variable came in first? Year. And then so what I have here is just the correlation in this kind of plot. So we're just using year, fitting a big tree with just year to the fit. What's the correlation between the fit and my approximation? Okay. So with one variable, you get this correlation. With two, you get that. With three, you get that. When do you stop? 3 or 4. Done. Done. Okay, outrageous claim. If everybody just did this and nothing else, it'd be a better world. What do I mean by a better world? They would actually find the subsets of the variables that actually matter, which is what they actually want, okay? You can't blame students for thinking those stars tell them what the important variables are. And no matter how often you explain to them, it's not that easy, they won't get it. For 2 good reasons. One, that's the problem they want solved. They don't want to know this hypothesis, this crap. They want to know what the important variables are. So you're just giving them the solution to a problem they'll care about. And 2, of course, the stars. Hey, come on, in grade 1, when I got 2 stars, that was better than 1 star. It's got to be the same as a grade 1, right? Yeah, how am I doing that time? You can stop me whenever. I could stop here, and you're supposed to be all excited about trying this.
Well, is anybody disturbed by the fact that color is the 4th one? The 5th? What is it?
Why would you be disturbed about that?
Well, it seems like it's kind of a weak. Is that real? I mean,
well, I don't know how much you know about cars. I mean, in practice, when you're working with the people who hired you as a consultant to do this, if they say, "I don't believe color is important," then a discussion ensues. That's absolutely right. It's a funny thing, statistics is most satisfying when you give them an answer that they go, "Oh yeah, I knew that before." That's the case where everybody's happy, but I've quantified what you knew before. But if you tell them something they didn't know before, then they get upset. That's true.
So not to get too much far into the weeds here. But so say you have a categorical variable that you've coded as dummy variables,
which is the case here.
But in some cases, wouldn't it make sense to treat them as, you put them all in together, all 4 dummies in together at the same time, rather than just doing one by one?
That's a great question. Absolutely, that makes sense. We should put that on our list of things to do. So right now, we just dummy it up, and the dummies are treated like anything else. But that's a great question. Absolutely, you might want to do that. And I have not written the software to do that. I got to try to remember. Put that on my list of, after I learn Python, Pybind 11, I'll do that. So, forward greedy search is kind of interesting, right? And that's how you build trees. So it's kind of a fundamental technology in data science. How do you do random forests? Well, you build big trees. How does each tree build? Forward greedy search. So in this example, I only have 15 variables, so I can compare. I can do forwards, backwards, and all possible subsets and compare them. But of course, as soon as you have like 30 variables, you can't do all possible subsets. So in this case, I can check and I get the same results from all 3 approaches. But you could argue that, well, 15 is a toy problem, Rob. Come on, get real. But I've done it with 60, and I guess I haven't done it with 5,000. So now I'm just reminding you, look, I'm not talking about inference here. I haven't got to that. And I still haven't really gotten to your question, which I'll get to in a second. But I claim this is totally different from what people usually do. I think if I just started with the application and said what I was doing to an engineer who knew statistics, they would buy it right away. And then my fundamental claim is if that engineer went out and did this, he would be better off in the real world than if he took a statistics class. The doctors have this ringing phrase, do no harm, right? Don't make the person worse off. So when you teach statistics, you always have to ask yourself, is the person actually worse off?
And this general procedure is not really specific to BART. You could do.
Oh, no, yeah. So up to now, the FHAT could have come from, say, neural nets. But so now I'm going to back up and say, okay, suppose I want the uncertainty. How can I do that? And then I really want to have BART. Okay. So I liked what I did. I jumped ahead and did the simple thing. But now we're going to go back and say, well, how do we use BART to assess the uncertainty? And actually, only then will I really give a good answer to your question. Well, let's see what this one. So step 3A was, okay, now that I have the subsets, now I'm willing to go back and actually run BART on all the subsets. And so what I have here, well, this is going, I was almost going to go back to the uncertainty, but this is a good, so just look at this column here. So what I have here is the FHAT, the fit. And then this is just plotting the approximation with the different subsets to FHAT. So if you only let me use 1x, that's how well I approximate FHAT with just that 1x, which was what, year, right? See how it's choppy? That's because it's year. But if you give me year and mileage, look at that. Oh, I'm liking this graph. I'm liking this. Just use year. That's how well you can approximate FHAT, which used everything with just year. Just plot them against each other. Come on. Oh, I'll let you use 2. How about year and mileage? Oh, look at that. With just 3 of the 15 variables, I can give you a function which approximates the function that used all the variables that well. See, that's a one-liner. You could explain that to anybody. Anybody can understand that. Anybody can do it. And you'll never get screwed. Okay, step 4, assess our uncertainty. Now I got to go back and use the BART draws, okay? But I like the way I just did it. That was good, right? To go to the application. Okay, so step 4. So I'm going to have a distance between f at x and then at the approximator. Okay, so again, now this distance is supposed to capture practical importance. There's no statistical significance there, right? Just f is the true function, and gamma at s is a function that just uses a subset of the variables. Okay? So again, if I explain it that way to an engineer, they're going to, well, okay, fine. Let's do it. Okay. Now, to assess my uncertainty, so there's a little bit of a switch here that's intellectually important. Now I kind of want you to put your statistician hat back on. The F represents what could be plausibly thought of as the true function. So ideally, you'd like to find an approximator to the true function, such that that distance is small as a practical matter. Okay? Well, you don't know the true function. I always put that in quotes when I say true function. So now I'm calling that a useful fiction. So before, to do my search, I just plugged in f hat for the true function. But f hat had all the variables in. Now what I'm going to say is, remember, FD is one of the MCMC draws that we talked about yesterday. And now let's suppose you didn't know any statistics and I didn't spend 2 hours boring you with what's Bayes. And I just said, look, I got this algorithm. It gives me draws of a function in such a way that they could be the true one. I have a bunch of functions. That set of functions represents plausibly functions which are plausibly the true function in light of the information in the data. Okay, so I just tried to summarize. So what's my Monte Carlo? I give you the data, you give me the data, I give you back a set of functions such that that collection of functions represents the universe of plausible, what could be the true function. Okay? Now, how is that? One line for what Monte Carlo is? It's not bad. It's not bad. Okay, and then you just look at all these distances. Gee, for every function, which could plausibly be the true one, how different is that plausibly the true one from my approximator? As a practical matter, and that's a distribution. So I have a distribution of the approximation error. Again, I could sell that to an engineer, right? And Mike West said, oh, no, you shouldn't be doing that. You should be doing this. How much farther apart, for every draw, how much farther is the approximator from the true one, plausibly the true one, from the f hat? So now f hats come back into the picture. Okay. So that's it.
And f hat is with all of the.
Yeah, all of them. Yep. I never, ever did variable selection in the usual way. That is, have some calculation of posterior probabilities on models with subsets or something like that. I didn't do cross-validation. I didn't do any of the things, ever, that we standardly associate with variable selection. Why didn't I do them? Because they're fundamentally flawed. Okay? So actually, let me, so you look at this. So I tried to translate that in English. Given the information and data, what is the likely size of the approximation error using only the variables in S? The approximation error from the true function to your approximating function. Isn't that obviously what you want? Isn't it? When I teach the MBA multiple regression and he looks at the stars, isn't that what he actually wants? Or I can look at this one. Gee, how much bigger is the distance from the true one to my approximator than the true one to my estimate of the function using all the variables? So that's the distribution of my approximation error. So here's where I get the uncertainty. Okay, so let's go back to the example. Okay. So this is the number of, so remember I have subsets for every number of variables. I picked a subset. I never picked a variable. I never said how important a variable is. I never tested whether a variable was in or out. Obviously wrong. I just have a, but I did a search in a pretty nuts and bolts. Hey man, let's just get this thing done way. And okay, is this search optimal? Can I prove that it's perfect? No, but get a life. I don't have time for that. Now I'm going to see if it worked. So I'm only allowed to use 1x. This is the distribution of the error. And here I'm using root mean square error. of how the difference between using a function with just the one variable versus using all the variables in the true function. Okay. So obviously that's the 50, so I just take the draws, I get the median of the draws, and I take does it say if they're 90%? 95% intervals. So remember yesterday when I first did BART, I get the columns. I just take each column for each X, get the middle one, get the half of 5%, half of 1 minus half of 5%, 97.5%. Okay, so that's a 95% posterior interval for the approximation error. And I finally am going to answer your question because it's crucial that that error is on an interpretable scale. So I could have just used the mean absolute error. That's probably that's an option in the R package, but it's root mean square. Let's assume it was mean absolute error. That's just the average error over the X's that you decided you were going to try to use this function at. Well, $5,000. Okay. Is that a lot or a little? You don't know because you're not working with this data. You're not a used car salesman. If you were a used car salesman, you would say, seems like kind of a lot. But on the other hand, the used car salesman might say, it'd be so great if I could just use mileage or year. 5,000 is not so bad. That'd be great. I'm going to do that. And my uncertainty is there. So I can honestly say, yeah, I'm pretty sure it's going to be, as a practical matter, about $5,000. If I'm willing to use two variables, there's the distribution of my approximation error. And I have to look again as a practical matter. As a practical matter in dollars, is that an error you're willing to live with? You can't do this without knowing what Y is. That seems like a good idea. If the variable selection thing works without you having to know the units of Y and the units of X, you need to be deeply suspicious. That trashes most of what we see, right? And then by the time you get down to, so this is the approximation error when you use all the X's. So that's like the distribution of FD, the draw versus F hat. So clearly, when you get down to 5 or 6, as a practical matter, the error between using the subset of variables and the error between using all the variables is of no practical importance. Incorporating the uncertainty, you're done. You're done. So what do you think? Okay, let's stop the talk. I got other examples, but I'm probably way over time, Rodney. Or you want to keep going? I don't know. Okay, that's it though, right? Okay, I can stop now. But how about, what I feel like doing? I feel like going back to my outrageous claims and do a gut check here. I think I did it. What did I want? Not hard to do. You run BART, you run these big trees, boom. No tuning, remember? I can run BART without tuning. Does it allow me to assess the practical significance? It forces you to assess the practical significance. Oh, it doesn't, because if you can just watch those distributions get down to that distribution and go, oh, yeah. So you can still be stupid if you want to be. And you can still get a good answer. So if you just watch those error distributions drop down to when they're in that other one, close to that other one, you do fine. But I like that idea of saying, gee, maybe I don't want to drive the error distribution down to the bottom. Because, see, if I was really doing decision theory, we'd be talking about the cost of measuring variables as part of our decision analysis, right? Allows me to assess the uncertainty. Yep. Correctly. Not that p-value crap. A scourge. Okay, how about the last one? What do you think about the last one?
No.
What? So I think the last one's, I think I got it. So if you weren't statisticians or statistically trained in some sense, I could have skipped a lot of the beginning. I could have gone almost right to the algorithm, explained it the way I did explain it to an engineer. No, I'm kind of cheating by using engineers, right? They're kind of my my people for this kind of problem. But I should really be saying an MBA. You should test it on an MBA. Not that MBAs are dumber, but they're just different headspace.
I have a question in the chat. So the question is, can we apply this method to a binary classifier? Would it involve transforming predicted scores into the log odds scale?
So the only issue that's tricky is the okay, so that D is the distance between F hat, between F. Let me go to this one. That D is the distance between the true function F and the approximator that uses a subset of the variables. So in my application, I used root mean squares because I had numeric Y, but I wasn't happy with it. That was too complicated. I said, gee, I wish I'd done just the mean absolute error. That's got to be more interpretable, right? So, but no problem. That's that's not a problem. So if I have a binary outcome, then the F hat would be a P hat. So I have to have a meaningful measure of how different the probabilities are. So I think this feels good. What do I have to change? My utility, my measure of how different things are as a practical matter. Is probably 0.65 different from 0.7 or not? Okay. So in the R package, of course, we punt and we use the callback library divergence as a generic distance between two distributions, which is okay for an R package. But it's written so you can put your own distance function in, because really you should be, right? You should be deciding. This is where you should be deciding what practical significance means, not the code. Hey, doesn't that sound good? Does anything else do that? But the default to answer the question, if you just ran the R package and you had a binary outcome, the default would be callback library divergence between the two probabilities. The two Bernoullis correspond to the probabilities. That's not terrible, but it's not as interpretable as even the root mean square for numeric. That's a funny thing in life, right? If it's a numeric Y, mad, it would be what I would do, mean absolute error. In categorical problems, even in deep learning, what do you use in deep learning for your loss? The cross entropy, which is the callback library divergence. So which is the log likelihood. So those things play a fundamental role in data science, for better or for worse. Maybe in PyTorch you can change your own. Okay, I'm done. I'll just say, let's just say what the other examples are, but I won't go through them. So maybe the next application is a binary outcome. Okay. So this is an application I did a few years ago. The Y is whether the next penalty in a hockey game is on a different team from the previous penalty. So we call it a reverse call. So I'm trying to predict which team will get the next penalty in a hockey game. Okay. And we got a bunch of variables. So I forget what we ended up after we dummied things up and stuff like that. So for example, there's a simple tree fit to the data. Remember, after all those things we've talked about, as a matter of just being a data analyst, just fitting a simple tree to your data off the top is a good That could be a healthy thing to do. So right away, I can tell you cool things like, hey, which team will get the next penalty depends on the score in the game. Okay, so if you're a sports fan, you're going to go, obviously that's true, but quantifying is kind of interesting. So even with a simple tree, you can find game situations where you're 72% sure that the next team that gets a penalty will be different from the previous team. In game situations where that probability is dramatically different. That's kind of a cool application. So there's my forward backward search. Some of it's 25 variables. That tells you which variables came in. They all make sense. So, but they all make sense. Oh yeah, I said I wouldn't do the application. Look at that. With 11 of the variables, you can approximate the thing just fine instead of using them all. There's my uncertainty, but to answer the question, I'm now using the callback library divergence, which you might not want to do. What was kind of funny about this one is, so it says use about 11. If you weren't going to do this, what would you do? I am okay with cross-validation. So what I did is I just looked at the out-of-sample prediction error using the subsets because I actually had a test set that I had left out and not used before. And I don't know, and it just turns out that you get the best out-of-sample prediction using the subset that we picked using our practical significance. Okay. So maybe I'll finish with, notice that they're intellectually two completely different things. Yeah, I did not do cross-validation. I relied 100% on the Bayesian inference that I got from BART. It turned out that when I said, okay, screw all that, I don't believe it, I just looked at out-of-sample performance. They lined up nicely. Okay, so it's intuitive to me that that's going to happen. I'm not the kind of person who has time to prove that because I have to learn Python. But it's interesting because intellectually, they're coming from totally different viewpoints. But because they both make sense, you end up with similar answers. Okay, I think I've, okay, let's stop there. But there is an R package on my web page. There's a little vignette on how to run it. It wouldn't be too hard to just try this. Oh. Do you want to just have a break now? Well, you're next, right? Oh, you're going to do the. I don't know. Now we don't have time. Why don't you just take a break and then just do the next one? You do that. We just go through the list and we'll stop where we stop.
All right, let's take a 10-minute break and we'll come back at 10:30 CDT.
You should stop me. But it is a little emotional, right? We live with this stuff every day, and some of it's crazy, and I still get upset about it.
It's a break. I'm going to stop recording.
What? Is that on the recording?
It's a break. I'm going to stop recording. All right, we're going to get started now. So first I'm going to talk about DART, which is based on the Dirichlet distribution. As I understand it, that's the German pronunciation, which is the way you're supposed to pronounce this. But most people say Dirichlet, I think. But according to Wikipedia, that's wrong. Dirichlet. Yeah. Anyways, so Dirichlet is a sort of a generalization of the beta distribution. You have these mutually exclusive probabilities that sum to 1, and you can have more than 2. So I have a bunch of slides at the beginning on different properties of the Dirichlet distribution, but that I inherited from Prakash. So because we teach a course together. But I'm just going to skip over these, but they're in there. They're in the slides for you to see them. All right, so let's talk about the DART prior. So effectively, this is BART with sparse variable selection. You can specify a Dirichlet prior when you're choosing the covariates rather than a uniform prior. So we represent it like so. So the S's are the probability of choosing each one of these variables, 1 to P, given some theta. And that's a we form a sparse Dirichlet prior like so. So we have theta over capital P as the arguments. And in the BART package, you say sparse equals true. And sparse equals false, that just gives you the default, which is they're just uniform, right? Everybody has 1 over P chance. This theta parameter can be fixed or random. If you specify theta equals 0, which is the default, that specifies a random value for theta that's learned from the data. The prior for theta is kind of an interesting looking thing. It's theta over theta plus rho is a beta prior. This parameter rho can be specified by the argument rho. The default is to 0, means that rho equals P, but you can override that. Similarly, there's a parameter B that defaults to 1, which can be overridden, and a parameter A, which defaults to half. And I'm going to talk about how to set these if you want more sparsity or less sparsity, or your heart's desire. So this distribution of this theta parameter controls the sparsity model. So A equals 1/2 induces a sparse posture, while A equals 1 is not sparse. So that's one example how to set it. And I'm going to show you some more on the next slide, or I guess at the bottom of this slide. You can also play around with this rho parameter. You can set it to value smaller than P. So here I'm going to show a graphic that shows you graphically what all these different settings line up to be. But at the end of the day, if we look at the bottom here, you can see that the non-sparse setting is 1, 1, 1. So in other words, A is 1, B is 1, and rho over P is 1. Okay, so that's not sparse. And then there's various sparse settings here, these 3. This is the default when you say sparse is true, but you can get more sparsity like so here. So let's take a look at the graphic. All right, so the way you look at this is that the height of these curves kind of give you an idea of how sparse they should be. And you can see the black line is the least sparse. The red line, which is the default, is here. But you can also get that, or sorry, yeah, actually the blue line is the default. The red line is very close though. So setting rho to be 1/2 of P is that. And then to get really super sparse, you set, you have the 2/2. So A is 1/2 and a rho is 1/2 of P. And then you get even more sparse. All right, so how do we do posterior computation here? This the Dirichlet draws our conjugate with the multinomial distribution. So the updates are pretty simple. What you do is you take the total branch count over the ensemble for a particular variable. So say the jth variable. So the count over the branch, for a variable j, the count of the number of branches on that variable, that's m sub j. And you just update like so. So that theta over p, you add m, and that's how you go along. This is a rich get richer type prior. Let's see. And these probabilities, these drawn probabilities, you can look at. They're returned by the BART package. So var count is the individual MCMC draws, and then var count mean is the mean over the posterior. Oh, and the probabilities are returned as well. Similarly, that's var prob. Now we'll talk a little bit about grouped variables. This is something that came up in Rob's talk when they were talking about, color of a car is really one variable, but how do you address that? And in BART, in Dart, if you just ignore it, you can get into a situation where these dummies are getting more emphasis than they should. So let's see how to fix that. So suppose we have capital P variables, but Q of them are encoded as a group variable, and by that I mean these are like dummy indicators, right? Like white, color of a car, black, etc. Right? So let's just assume these are the first variables. However, you can do this for multiple group variables, but it gets a lot harder to show that. But it's trivial, really. It just harder to harder to make a slide out of it. So the variable selection probabilities are S. So there are two other probability collections of interest: the collapse probabilities. So the collapse probabilities look like this. So in the first entry, we have the sum of all of those categories, and then after that, we have all of the others, all of the other variables. And then there's something called the rescaled probabilities that look like so. So such that these sum to 1. And all of these ideas come from those properties that are at the beginning of the talk, which I skipped, but it's just probabilities of the Dirichlet distribution. So if we just blindly use the probabilities, blindly use the dummies, you would get something that looks like this, right? And you would see this, you'd have this large weight on the first entry, right? So you'd have Q times that, which we don't want to have, right? We want to reduce that P1, in this case, the first one, because it puts too much emphasis on the grouped variables. Well, that's fairly trivial. All you have to do is rescale them accordingly, like so, and you get a reasonable inference. So in the BART3 package, this is what the default is. In gbart, when you say sparse equals true, it does all that for you automatically. If you use a data frame and you say that the group variables are factors, right? It sounds easy, but that it took us a while to create that nice feature. So now you have it. So Dart was a big breakthrough, I think. However, it's not truly variable selection in the usual sense, it seems to me. There's no, So like, what is the cutoff, for example? How do you know when to say, okay, this variable is important and that variable is not? It was, so recently, something called Thompson sampling variable selection came out that sort of operationalizes those decisions. And I just have a sort of abstract slide here about Thompson sampling variable selection. So I'm just going to kind of read this out loud. So, a variety of methods for variable selection with BART have been demonstrated. The original variant importance that was in the original paper by Rob. There was a permutation-based VIMP that came out soon after that. The decoupling, shrinkage, and selection idea that Rob talked about, the fit, and Linero's work, the Dart stuff, and then now we have Thompson sampling variable selection. Well, what is it? So it has some attractive features above and beyond all the others. At a high level, it's kind of a natural progression of VIMP. It stochastically searches the covariate subspace as DSS does, but DSS doesn't do it via VIMP directly, right? But TSVS or Thompson sampling does, and it can be formed either with or without Dart. So in my mind, TSVS is kind of a unification of the current state of BART variable selection. And it has a solid Bayesian, pseudo-Bayesian theoretical basis based on something called Thompson sampling. And we don't really have time to get into all the bells and whistles of what Thompson sampling is. I have some slides. I have some slides on the theoretical basis. I probably skip over most of those, but let's talk about what Thompson sampling variable selection is. So it's a stochastic optimization approach to subset selection based on reinforcement learning, extending Dart, extending the Dart idea based on Thompson sampling. And there's a nice review of what Thompson sampling is here for a reference. So basically, it's a multi-arm bandit problem where each variable is treated as an arm, and you can pick multiple arms at the same time. It's effectively, you're searching the subset space. Okay. So if we have our model like this, it determines an optimal subset, or I say the near optimal subset, SO, with the cardinality Q0 that have an impact on have the optimal impact on the fit. Now, what does optimal mean? Well, there's that gets into Thompson sampling, but it's a pretty straightforward. I'm going to show you what the algorithm looks like in a moment. So these variable inclusion probabilities have beta priors, like so. And then this gamma j is a reward if xj is chosen. And effectively, that's just a 1 or a 0. Okay, so that's a Bernoulli. And then this unknown mean reward is the inclusion probability. So it's the expectation of these, okay? So it's just theta. And like I said, now there's a bunch of slides on how this works from a theoretical basis. But I don't think you need to know that to use it. So this is kind of like maybe Rob's idea, where you don't need to know all of the ingredients to enjoy the meal. So I'm just going to skip those. So another nice thing about TSVS is it works with big N. What do I mean by big N? Well, it works with data sets that are so large that you can't actually fit them, where you have to fit them in chunks. That is a nice feature. I'm not really going to talk about that, but that's like an added plus that you get from this method that no other method I know of that will work with that easily. So I'm going to focus on just big P, which is the usual problem we have, which is a lot of variables. So you have to initialize some constants at the beginning, and we have software that does this in the BART package. But just to explain what's going on, the ones that really seem to matter the most are M and T. The rest have smart defaults, and we love that, right? And BART, smart defaults are everything. If we didn't have smart defaults, we wouldn't be sitting here today talking about this. All right, so there's something called C hat. Typically, that's just a half, but you can get into the theory and you can come up with possible other choices, but a half seems to work pretty well. So L, length of the Dart chain, burn-in, discarded. So what I didn't say is, so in Rob's way of doing fit to fit, each one of those fits are done by a tree, a fast fit. Well, that's not the case here. Actually, each one of these trees are a BART fit, typically a Dart fit. So it can be a little time consuming, but on the other hand, with multi-threading, actually it goes pretty quick in most cases. So L is the length of the chain, the burn-in, discarded, and M is the length of the Dart chain to keep. So one thing I didn't say about Dart, and I think it's sometimes not well recognized. I was just getting to that. I'm just getting to that. All right. So what I think the mistake people make with Dart and maybe variable selection in general is typically for Dart, it keeps learning as you're searching the space. So when you're doing Dart, typically you want a long burn-in, maybe we shouldn't focus on the burn-in, but you usually have a little bit slightly longer burn-in, but a much longer run of the chain. And you can't break that up into like, you can't break up the chains. Like, the Bayesian trick is to make this faster, you run a bunch of shorter chains, right? To make your posterior. That doesn't work with Dart. Dart it needs that long chain to learn because it's constantly searching the space. So that's did that answer your question? Oh, okay. Right. So yeah. So I just have a note here. So M. But we'll see. M doesn't have to be crazy long. It just has to be long enough. But how long is long enough? Okay. The number of trees. So typically you have a small number of trees. I don't have this in red, but I probably should have. So what I found is changing the number of trees is very helpful. So like for example, like in Rob's example, he's got the year of the car, right? Oh, come on, everybody knows that, right? but I'm saying so sometimes when you do this, if you have H set to 10 trees, you just get the year of the car, right? I don't have access to that data set, so I couldn't try it, but I'm going to show you another data set where we can compare. But what you can do is you say, oh, wow, I want more. So you just add more trees. right? And that was kind of like the original variant importance that Rob had in the first paper. They just added the number of trees and they just graphed it along. You do exactly the same thing with TSVS. The number of steps. Now this is a sore issue because Lou and Rakova say the number of steps should be pretty big. Like they'll say like 500 steps, but I haven't found that. I like usually 20 is plenty. So so I'm not sure. What they're getting at there, but I mean, this is recent research. This came out 2 months ago in JASA. So I mean, this is pretty cutting edge stuff. But I mean, we've been using it for years because we got because it was an early release in JASA. So as you're going along, you fit the data set once because you're going through all the subsets, right? So you fit it once, you fit the data set again with a different subset. You fit it. Those, yeah, those are the subs. Yeah. And then we have these parameters of that theta distribution, the distribution of theta, and for each one of the parameters. Okay, so this is what the algorithm looks like. So this is exactly, so right here, so you have T steps, and for each of the variables, you're going to draw that theta randomly, and then you're going to create a subset based on that where those are greater than C, and C in our case is greater than half. So anytime your probability is greater than half, we accept it. And like I said, a half is based on there's some reasoning why that should be an optimal choice, but you know, you could play around with that if you really, like Rob was talking about, the cost of different variables. So if there's a way of factoring that into the choice of C, but in this case, you know, most of the times when I get data sets, they're all free to me, so I use them. So you're going to fit a Dart model at each step. With these XT and by the T, I mean, that's a subset, right? So no, all the way to M, whatever M is. So M could be 2000. Well, no, well, I mean, okay, the burn-in, so remember for Dart, the reason L matters, which is the burn-in, is because so the way Dart works is it needs to have, you know, when you were looking at that convergence of BART, you know, like towards the beginning, it's really way off, right? You can't start Dart right away. Dart needs to start a little bit later. So that's why L comes in. Usually L is set to like you had end skip is 500, right? Yeah, probably. yeah, probably. But the problem you're going to run in there is if P is big, you really want Dart, right? So it's worth it, right? But if you have like a small number of variables, like I don't know, like you had like 15, yeah, you could run BART. Okay, so yeah, so these are subsets, right? And then you figure out the rewards because you got to figure out what you're going to do in the next step, right? So if it's not in the subset, then the reward is 0. Else you calculate the reward, and how you do that depends on whether you're in a big N or big P situation. So I'm going to talk about that on the next slide. But anyways, you update these parameters like so. So A gets added that. B gets added 1 minus that, and then you calculate those probabilities. The important ones are greater than a half, et cetera. Then you go into the next T, or until you just, yeah, you keep going until T, right? But like I said, T is usually pretty small. All right, so this is what they call offline. So offline is the machine learning codex or whatever for big P, right? Have you guys heard this offline? So, so that's what they call it. So So now there are no limits on P. P could even be bigger than N. So typically M is 1,000. So it's not enormous, right? Let's see. Oh, so this is about how you set the reward. So if J is in ST, then the reward is 1, okay? If the corresponding mth draw has picked that variable, right? If it didn't pick it, you get a 0, right? If you pick it, you get a 1. So in other words, you know, these are like this, oops, sorry. These are the same kind of things, branch tree counts that we were talking about earlier for Dart, right? And like I said, they recommend T is 500, but I don't know where they're getting that from. 20 or 50 is fine. Now, I also have it on here for what they call online. That's where N is bigger than P, but N is big, right? So you have to actually shard the data sets. You can't run the whole data set together. So they have some advice for that, but I'm not going to talk about that anymore. It's here if you want to read it. All right, so this is this is not the famous diabetes example. This is a different diabetes example. Diabetes and recurrent hospital admissions. So we've got a cohort of newly diagnosed diabetes patients and their hospital admissions, occasionally multiple admissions from a single healthcare system. We have their EMR from 2007 to 2012. Records may or may, before that, records may or may not be available. As we all know, EHR is an omnibus of digital healthcare information, lots and lots of data, right? So we had access to 84 covariates. One of them is time, number of previous admissions, patient demographics, health insurance, healthcare charges, diagnosis, procedures, anti-diabetic therapy, laboratory values, vital signs. So lots and lots of different variables. By its very nature, EHR is a fundamentally time-varying omnibus or corpus, whatever you want to call it, because things are changing all the time, right? Your vital signs are changing, your labs are changing. However, one challenge we ran into is the EHR covariates are occasionally missing at time 0, even if we carried the last value forward. So we used, there's this imputation technique that we found very useful called sequential BART. So you guys look that up. It's on CRAN. It's an archived package on CRAN. So it's not currently available, but like if you look in the archives, you'll see that there's.
Excuse me. Can you explain the time 0? What does this mean?
Time 0, let me see if that's coming up. Time 0, I think is, I think it's like 2007. Yeah. So that's why I said we're following these patients from 2007 to 2012 for 5 years. So prior records are typically available for most people, but they're not necessarily available. We have data from 2007, 2012. We may have earlier data or not, right? So that's time 0. So we had 488 patients time 0 is 2008. So we had 1 year available prior to 2008. The survival rate was really high. So pretty good survival, 94%. But hospital admissions were more than 1 apiece, 525 total. So for a relatively healthy group who almost all survived, they got admitted a lot in 5 years. More than 1 per person, right? So we wanted to know which covariates increase the risk of admission. We can't do something about all 82, right? We want to know just what are the important ones. What about the number of previous admissions, right? Is that important? Or an acutely recent admission? Does that matter? What are the functional forms of the covariates? Are they linear, quadratic, logarithms? Are the covariate effects additive or multiplicative? Are there interactions? So we wanted to avoid all those types of pre-specifications, so we used BART. All right, so here's what the data looks like. Most of the patients didn't have any admissions, 63%. What I'd like to focus on is these patients down here. If we could figure out at time 0 who is likely to be in this group with 4 to 16 admissions, notice they had 331. They had 63% of the admissions. Just 51 people. That doesn't even seem possible. These people have a lot of up to 16 apiece. I mean, that's wild. In 5 years, so you're coming in a lot. You like to have your own room. So I don't know. I have some variables here. I don't know if we have time to go through all of these. Let's see. I don't know. I've got the usual suspects on here. Virtually none of these really matter. But I mean, it just gives you an idea of what. I mean, these aren't the super important ones, as you'll see. Yeah. All right. So, like I said, we're going to focus on the 84 covariates. So I randomly divided into training and validation sets. In the paper, we used fit to fit DSS. But today, I'm going to show you what does TSVS do. So we have a nice comparison here, a nice head-to-head comparison. So DSS found these, serum calcium. And you know, this is like when Rob was saying earlier, you have to know your data, right? So when we talk to the physicians, we say, look, this serum calcium keeps coming up. And they're like, well, we don't know what that means. So if you have diabetes, I would check your calcium because it seems to be really super important, but nobody seems to know what it means. But the next one, peripheral vascular disease, they said, yeah, I think, well, okay. So this is the way the conversation goes. You say, you know, serum calcium looks like really important. They're like, oh yeah, if this happens, then that, you know. So it's just like they didn't really have that one down. That is like the most important variable. So what I think could be happening is maybe it's selective. Like let's say you have diabetes and you're in this high risk group. Maybe you're getting monitored a lot more and you have a lot more high values. I don't know. Nobody had a good explanation for this one. But the others, they did. So when I said, okay, peripheral vascular disease, they say, yes, peripheral vascular disease. So what happens is when you have diabetes long enough, it like ruins the vessels in your fingers and your toes, and they call that peripheral vascular disease. And if it gets really bad, it's really bad. So typically that means you've had it long enough. You've had it for a few years. Now I said that these are newly diagnosed patients, right? But maybe these patients had a really bad case because they developed it really quickly, right? Or maybe they've had it longer than we thought. We don't really know, right? The EMR, they always say, oh yeah, well, let's look in the EMR and find stuff out. Well, the stuff you want to find is sometimes not in there. Number of previous admissions, they're like, yeah, duh, we knew that, right? So like these people get into a cycle where they're just coming in a lot, right? To come in 16 times, you've got to, they know your name, right? They know who you are, they know you. Then the others, I don't think they had a good sense of. The other two that DSS picked up was insulin treatment and peptic ulcer disease. Yeah, that's what yeah, sorry, I didn't say that. Yeah, so if TSVS picked up those as the top three, I mean, after I saw this, I'm like, you know, I think serum calcium is, you know, I thought it was important back then, but what do I know, right? I'm just, you know, I don't know anything. But TSVS also picked up some others that I thought were really interesting. Blindness, cardiomyopathy, And that means your heart muscle is weakened, typically. Creatinine, gangrene. Now this is gangrene. So this is what I was talking about with PVD. So a lot of these people end up with gangrene because the vessels in their toes and fingers, they don't get enough oxygen. That's bad. And then something that people were always, I should say, these 84 covariates, they weren't picked by me. These were picked by medical experts, right? So even though we said serum calcium, but they put it on the list because they were like, it might be bad, right? Or it might be good. Yeah. Yeah. No, it narrows it pretty quickly. And there's something called relative value units. This is something that they were saying, this really matters. So what this means is, how much care are you getting? Like, okay, let's say we do something to you, whatever the procedure is, but how intense is that care, right? Like a Band-Aid is really low intensity, right? Whereas a cabbage is high, right? Coronary artery bypass, so how intense is it? And they said TSVS says that's important. TSS didn't pick that up, but it's all relative. But I can tell you what, these two are super important, right? And they're on both lists. And this one, I don't know. I think there's something to it, but like I said, what do I know?
So, quick question, sort of just a practical question. What happens when some of these variables are like potentially highly correlated with each other? Is it like lasso, or just kind of picks one of them, or how does it work?
Yeah, that's a good question. So BART is really, I want to say, robust to this. Like you can put in the actual outcome, and BART doesn't pick it all the time. So BART is, I wouldn't want to say immune to that, because you still have some issue. But BART is pretty good about, if X1 and X2 are really highly correlated, it's pretty good about picking them both. Now, go ahead. You got to get on the microphone, Rob.
That's the way I did it. It would pick one of them, but hopefully the best one. What? Is it? Oh, so that's always a great question. So obviously the way I did it, it's gonna pick, if there's two that are highly correlated and you need one of them, I'm gonna pick one of them. And the only way, if I just do the forward search, backward search, you're not gonna be aware of that. If you look at we did do stuff where we looked at all subsets and tried to figure out, after that. That's always super interesting, but it's always super difficult. But clearly, the one I presented is going to pick one of them. That's an issue. So what about TSVS? Seems like they could come in and out.
Well, the reward is just if they have both, right? So like if we go back up to look at the reward, right? Excuse me. The reward is just that they're both in the subset, so.
Because the flip side of it is, so the way I did it, it's going to focus on a few. And if the software currently is not telling you that, oh, gee, I'm loving X5, but you could have used X7 as well. It's not telling you that. And sometimes people really want to know that. So that's a big issue. The thing you worry about is also the effect. If I put in a bunch of X's and they're highly correlated and you could have one of them, then the marginal probabilities for each one can get low. So, the joint distribution would tell you need at least one of them. If you look at the marginals, I don't know if there is one support to deal with that. It seems to me like the TSVS is going to suffer from dilution. in the sense that if you had a bunch of highly correlated ones, every time you go to refit your dart, different ones can come in and out. This is obviously a fundamentally difficult problem.
And it's tough when you have 84
The table was saying, well, I'll tell you one to use. Don't worry about it. And depending on the application, that could be good or bad.
I mean, it's tough too. You have 84 covariates. Some of them are going to be correlated. So it's like, I don't know. Yeah, maybe there's no good answer to that one.
In this application, this is a great application from 84 to like 5. It's going to be pretty easy to figure out what's going on. But if you're going from 84 to 40, and there's a lot of correlation, that's a serious problem. I'm not sure I'm confident that I know how to deal with that.
Can I?
Oh, go ahead.
Can I add a more question regarding this one?
No, no more questions.
Yeah. Sorry. Yeah, this is actually making me think about this, particularly, for instance, let's take a medicine, beyond medicine in stock market, right? Particularly, we have a bunch of stock. Some of are positively correlated, some are negatively correlated. So I'm wondering whether BART or other tools you are developing, they can differentiate this is a positive or negative associated.
Yeah, once you pick those variables, I can show you what they're peripheral vascular disease is worse. I don't know if that I have it in this slide deck, but actually we're going to talk about this later if we ever get to that talk.
Unnatural. Once you get it down to 5, then you could do those versions of partial dependence plots, right?
Right, and that's exactly what I have. So if you look in the time to event talk that I'll be talking about this afternoon, you will see plots in there. So yes, this doesn't tell you if they're bad or good. It just tells you they're important.
Thank you.
You're welcome. And in the so I just updated this the other day, how it creates the plots. So this is what the plots look like. So these are the inclusion probabilities. See, they move around a little bit, and these are the VIMP probabilities for the subsets, the choices. And you can see the calcium, PBD, and N are all way at the top, right? Those are but there's those, and these are the rest, but those are like sky high. The VIMP probability is almost 1 at 20 steps. That's pretty amazing, right? Okay, that's all I wanted to, go ahead.
I'm probably not going to get around to giving a talk that's on the list, which I probably won't have time to do. There's a topic there, monotonic part, and monotonic discovery. So let me just quickly, that is. So,
oh, sorry, I fucked it up.
So it's constrain the variable to be to the function's monotonic in that variable, so it has to be going up. So that's okay, but it doesn't answer your question. What we do is we put the variable in twice. Put the same variable in twice. Once it's constrained to be monotonic up, once it's constrained to be monotonic down, and then you do variable selection, and you find out right away which ones it's always positive, which ones it's always negative. So
actually, that's.
I really like your question because you're right. So I say, well, variable selection is important. Which variable is important? But of course, you're going to wonder, well, but is it good or bad? And then that's difficult because as soon as you have interactions, the answer is, well, it depends. So I liked your question a lot, and your question, because that really gets to fundamental things that in practice people are really going to care about. I mean, they still love the linear thing. Oh, well, what's the great thing about the linear thing? Oh, I can just look at the sign of the coefficients. Well, if you're a little bit smart, you can still have to worry about how big it is, but still, you want to know, is it a positive or negative? And so having tools where you can get that information out of the models, that's super important. And that's why Rodney talked about the added variable plots yesterday, but they're fundamentally flawed too, because you don't want the average effect, you want the conditional effect.
Right.
Great question.
I can follow up with you
I have a talk
after
I'm
this
not
meeting.
going to give, but I have kind of an answer, but that's research. We haven't really,
Right.
that's kind of new stuff.
Thank you so much. I can talk with you later. Yeah. Thanks so much.
Rob, actually, that was the last slide. So I was going to take questions. Why don't you start talking about monotonic BART? But is there any other questions? Wait, wait, you don't have your microphone on.
Wait, can I ask one question here?
Yeah, sure, go ahead.
One of the things with Dart is that there is no dependence on the number of trees. So if you kind of set the number of trees to be really, really large, it's possible that after a while you just start introducing some spurious splits, and that'll get picked up by the Dirichlet multinomial. I'm curious if Thompson sampling has like an implicit dependence on the number of trees.
Yeah, it does. So like I said, you typically start small. And then, like I said, if all you're finding is, yeah, I get the year of car make. Okay, yeah, okay, obviously. If all you're getting is the silly easy ones, then you just start expanding the number of trees. And we have a paper out. Like I said, if I ever get the chance to talk about that this afternoon, we have a paper out where we show, okay, start with 10 trees, then you do 20, then you do 30, and you see what happens. And you get the more subtle effects, right? You go from the earth shaking effects to the little subtle effects to then this, okay. Put your mic on.
When you said that when you run the TSVS, you do go for use smaller trees.
Yeah, yeah. In the paper that you and I just published last month. you forgot about that. No, they just set it to I think 10. But I knew that from your paper. So I already knew how to do.
Because that was our basic finding in our simpler method.
Yeah.
But I guess I'm curious whether these methods don't have that property where. So let me just review. So if you just run straight BART, you can just look and see which variables are used in the splits. And that seems like an obvious way to do variable selection. And it is, but what happens is, maybe what Samir just said is if you just run it with 200 trees, well, lots of things come in spuriously that, they come into a split, they don't really do anything, but they're there.
And it has to pick something, right?
Okay, they're there, but they're not really doing anything. So let's get rid of them. That's what my method was, what I just talked about. But what we found when we first did BART was, well, if we just use fewer trees in the ensemble, then it focuses on the important ones. And then you can just look and see which ones are being used. And that actually works pretty well. So that's super simple. That's worth noting. And that's in the BART package. You get the variable count out. And the only thing you have to know is, but it's a little bit annoying because you go, well, if I want to predict, I should use 200 trees. But if I want to do variable selection, I should use 30 trees. It's a little unsatisfying. So I'm curious that Rodney's reporting that with the TSVS, that there's still some of that in there.
Yeah,
Which, not surprising, it makes sense. Because, you're going to run BART or Dart until it burns in and maybe for a little while longer. And then you just look, you're still just looking and see which variable is being used. And that's all you're doing.
Yeah.
So you're still gonna have this basic property that if my ensemble has 500 trees, well, lots of things will be in there that really aren't doing it.
Yeah, but they don't get a high weight in the, if you look in the plot, I'm only showing the ones that are important. There's, yeah.
They won't come in as often.
Yeah.
but it'll happen, everything will happen faster, harder, or quicker with a smaller number of trees.
Right, exactly. That's exactly right. That's exactly there. The smaller number of trees. Yeah. All right. Did you want to talk about monotonic BART now?
So this is research, right? We're trying all these different stuff. And, what actually works the best? Well, come back in 5 years. We'll tell you how we feel about it then. But again, I really like your point because it's what I try to stay focused on. What are people going to actually care about an application? And, which variable is important? Yeah, they care, but they also care about the sign. But as soon as you have nonlinearity interactions, what does the sign mean? There's an issue there, how you're going to design software understanding the things they want.
You didn't want that to be. All right. Should I stop sharing?
Yeah, you have to stop there.
Okay. You're there. Oh, so. Wait, nobody's sharing.
When was the first BART paper? Was it 2010?
All right. Are you going to use your walk around microphone?
I can just do page forward, page like this.
Yeah.
Okay. Is there a pointer? Is that a pointer? Well, I can't point. Oh, that, okay, fine. 'Cause I only have, okay, this time I'll only do like 20 minutes, okay? So forgive me for going on too long. So I'm gonna start off from a different place than you were, but I claim I'll end up back where you were, okay? So I'll start off by saying, let's be Bayesian again. We want to use prior information, but I want to be flexible with the function. So what kind of prior information might you have about a function? Well, you might have the prior information that it's monotonic. So how can we run BART and impose the constraint that the function is monotonic? So that could be your prior information. You just, come on, I know if I increase the x's, y is going to go up, please. Okay. So if you have that valid prior information, why would you want to impose it? Well, if you're right and you go to predict, you should do better. If you're right and you look at your uncertainty, that inclusion of that prior information should reduce your uncertainty because you've added that knowledge in. Okay. So contrasting into the linear model situation, if you knew a coefficient was positive, maybe that would be a super helpful thing to put a prior in that said, come on, I know the coefficient's positive, don't. But now we can generalize and say, I know the function's monotonic. Okay. So now my headspace gets to revert to the, now I'm a hardcore Bayesian again, right? I have prior information. I want to include that prior information. Okay. So this is a great picture. So there's my simulated data. And notice I have fewer observations on the left-hand side than the right-hand side. And the left-hand side, I just ran BART, just like yesterday when I did my first example. And oh, look, I was a little bit cooler about how I did the 95% intervals. So the gray is the 95% point-wise intervals for the function. Okay, so forget about the right-hand side for a second. Just look at the left-hand side, and it's just like yesterday. Just basic BART. And then you're supposed to feel good about it. Look on the left, I have a few observations. Look how my uncertainty goes up. It looks very reasonable. What else? How else would you do this? Forget about it. Okay, but suppose I knew that the function was monotonic. And I did all the BART ideas we talked about, but I imposed the constraint that was monotonic. Then I get the inference on the right. So overall, so there's lots of things, there's a few things to see. Again, the fit is good. It looks better on the right because it's monotonic. And Rodney mentioned this yesterday. Because it's monotonic, you get a little bit of smoothness. Okay. So one thing, even random forest, boosting, BART, you do kind of get the squiggly. When you look at the posterior mean, you have the squiggly fits. And sometimes people just don't like that. And I'm like, get a life, come on. And it's the squiggle compared to the noise is nothing. When I go to predict, it's not going to matter. But it upsets people, right? They go, no, it's not. I don't like squiggly things. So, because I knew it was monotonic, it reduces the squiggle. Clearly, again, out of samples, not going to be that much difference. But it also reduces the uncertainty, right? Because I knew it was monotonic. So there's no up and down. And again, you have the nice property that the uncertainty is higher on the left and the right because you have less data. Okay, so it's just it's a variation of BART where we're able to run the MCMC, do everything, but impose the monotonicity. Okay. So in basic BART, like yesterday, I could put up the 1D example and I could a little bit shakily, but not too crazily say, hey, come on, guys, with lots of X's, it's the same damn thing. there's a bit of an issue. What is monotonicity? With 1x, you know what monotonic means. We have to be a little bit careful to say what monotonic means with more than 1x. It's not going to be complicated, but there's a little bit of a issue to be clear about. Okay, so here's the simple observation makes the whole things obvious. So at first you might say, well, that's not going to be obvious how to make this ensemble of trees monotonic, blah, blah. There's lots of stuff going on. And then you just go, well, if the sum of two monotonic functions is monotonic, so if I make each individual tree monotonic, then the ensemble will be monotonic. Okay. And then, it's a little bit of work, and I'll show you some of the detail, but because trees are not that complicated, we can figure out how to impose the monoticity on a single tree. Okay. Okay, so what's a mod? So now we can live with one tree for a little while, but we know this is going to work with the ensemble, the sum of many trees. Okay, so here's our back to our basic. What's a tree? So here's a tree, and I want to look at that tree three different ways. There's the tree. There's the partition in. Sorry, so I have x1, x2 bivariate. So there's the tree that corresponds to this partition of x1 and x2 with these mu levels. And maybe since there's only two x's, that corresponds to that function piecewise. That might have been a good plot to have yesterday too, right? If you're first time. Not a bad plot. Okay, so I claim that tree is monotonic in x1, x2. Okay, so what does monotonic mean? Maybe that's, it's always fun guessing what the next slide is. I can never remember. Usually I have a hope of this is what I was hoping for. So all you're saying is with many x's is monotonic and all the x's if fix all x's but one, anytime you increase xi, then the function goes up. Okay. So, that's obvious. One obvious way to define monotonicity. There probably are other ways in a multivariate setting, but I think that's got to be the one that people mean. Okay, so, this sounds a little bit like your question now, right? Gee, you'd like to know if you're monotonic in a particular variable, no matter what the other variables were. So I want to be able to express this monotonicity idea in tree language. With just one variable, it's straightforward what you're going to do. So here's my monotonic fit of a single tree to some data. And each one of these flats corresponds to a bottom node. And how do I constrain this thing? I go, well, for this bottom node, this mean has to be bigger than this mean, and it has to be less than that mean. Okay. So the way I'm going to think about the constraints is every subregion has neighbors, and I just have to look at the neighbors and make sure that the monoticity is correct in terms of the neighbors. Okay, so with 1x, it's easy. I just look at the interval below me. Well, I need to be bigger than that. I look at the neighborhood above, next to me, bigger than me. Oh, I have to be less than that. Okay. So I just need to take that idea and express in a way that will work for any number of x's. Okay, so with two x's, so this would be a partition of the x1, x2 space corresponding to a tree. So, and then I have the node number there. It's probably the right, I don't know if that's, That looks arbitrary to you, those node numbers, but they identify those bottom nodes. So the code, the C++ code does stuff like, oh, look at bottom node 7. Bottom node 7 is disjoint from 4. You can't increase a single X and get from 4 to 7. So the mean level in 4 does not constrain the mean level in 7. Okay. I can get from 13 to 7 by increasing one of the, just X1. So the mean level in 13 will constrain the mean level in 7. Okay, so you just have to go around and see what are the neighbors. And, you know, and so it's not too hard to write the C++ code with any number of X's. With 2 X's, you can see what's going on. So the mean level in node 7 is constrained by the mean levels in 13, 10, 11, because those are neighbors that you can. So what does a neighbor mean? I can get from that region to the region in 7 by increasing one of the variables with the other ones held fixed. Okay. So that's how you compose. This is a little bit interesting to me because if you just treat it like a mathematical problem, what's the constraint space? You just go around circles, it's confusing. But if you say to yourself, I have to write code, then I think it becomes, the algorithm becomes quickly apparent. And the other thing that's fundamental here too is the basics of the BART MCMC that we talked about yesterday are going to change. Because if you remember yesterday, I think you were asking, oh, gee, how do I draw the TM? I said, well, I'm going to integrate out M. Those the mean levels. So clearly what we're talking about now is that M space is constrained. So now if I was going to try to integrate it out, I'd be integrating over that constraint space. Trying to understand the full multivariate constraint space, what the set of mu's are given a partition, that's actually hard. Yeah. But what, okay, you don't think it's hard? I think it's hard. And integrating over that space. What's easy is for any one mu, figuring out how that mu is constrained given the other mu's in the neighbors. That's what I just argued. So that's going to lead to a fundamental change in the MCMC. We're no longer going to integrate out all of M and do a move in T, and then after we do a move in T, draw the M. We're going to heap all the M's, all the mu's in place, and just when we do a growth, we're only going to play around with the 2 mu's involved in the children. And they're going to be constrained given the other mu's from the other nodes. Okay, so maybe you can figure out the multivariate constraint space. Well, what I know is if you give me all the other mu's, I can easily figure out my constraint space for 2 of the mu's when I do a growth, birth, or just 1 mu when I do a death. And then I'm just working either with a 2-dimensional space, 2 mu's when I do a birth, 1 mu with when I do a death. I can figure out the constraint space and I can integrate numerically because I'm only doing a 1 or 2-dimensional integral. So that's the technical part of it. Okay. So it was a little bit interesting for us because we were in love with this integrate all out of M to T, and we had to let go of that. So I won't. So I just explained the whole thing to you. That's all there is to it. So let's see how much we can skip now. Okay, so I think this is what I just said. For any bottom node, you can easily figure out the constraint interval given all the other nodes. Okay. Because we're just making local changes, in particular for, say birth, death, you're only working with 1 or 2 mu's at a time, and you can figure out the constraints on those 1 or 2. Okay. I don't have to think about all the mu's. Okay, so now we just go back to BART, and I say, okay, I'll use most of the ideas I talked about yesterday and setting up the prior and doing all this stuff. And I'll just say, okay, my monotone bar prior is the old prior times an indicator that it has to be monotonic. That not the function has to be monotonic, that each tree in the ensemble has to be monotonic. Remember, theta involves all the trees, all the bottom node mu's, and everything. Okay. Okay, so that's too much stuff. Let's skip this slide. What that slide says is that when we do the when we propose a change, we don't integrate. It's not just in tree space. We have to keep all those other means hanging around. So the notation is like there's M common, M old. So N common is all the other mu's. I got a condition on them. So I'm just going to pick a small 1 or 2 mu's to play around with so I know the constraint. Okay, so that's a fundamental change in the algorithm. Well, maybe, or not. It's a small, or just a small change, depending how you feel about it. Okay. I'll say this: it's a, like now it just seems completely obvious the way I'm saying it. I think it took us a while to figure this out. It's really funny sometimes when you do research. I think, but maybe. I'll say this for myself. I don't know about you, but sometimes like the most obvious things, you take like a long time to figure it out, and you're like, should have figured that out faster.
Can I ask a quick question with that, with this M nu and whatnot, because you've got this constraint? Are you gonna just use some like numerical approximation, and do you correct for that error in your Metropolis Hastings?
What error?
You can't integrate everything out completely. So
remember, I'm conditioning. I'm only doing integrals in 1 or 2D.
Okay.
So I do them numerically, and there's virtually no error. Okay. 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 So a few simple examples with pictures. So I'm going to try to estimate the function y equals x1 and x2, but x1 and x2 are constrained to be in 0, 1, so it's monotonic in both x1 and x2. Okay, so there's 2 plots of the monotonic function. The one on the left's not bad, those contours, see? The one on the right, looks like I should have rotated that a little bit. That's not the, but anyway, you can see that's the plot of f of x versus x1, x2. It's monotonic. I feel like I should have rotated it. You see them. Okay, so I fit a single tree to it. And I think I used my Bayesian software to fit the single tree, but I could have done it with card, however I did it. I fit a single tree to my simulated data. And see, there's the 2 plots of the fit from the single tree. So function. So I don't know. Yeah, I guess you could say it's not terrible, but it's, what's the technical term now? Jumbly, bumbly. There's lots of little regions where you go, I don't buy that. That might be a little hard to sell to your client. It's very funny. Like in my mind, in this talk, I'm thinking, oh, look how terrible that is. But right now, looking at it, I'm going, that's not bad. Forget the whole thing. This is fine. I changed my mind. So here's the fit with a single tree, but monotonicity imposed. Okay. So that looks noticeably better than the non-monotonic one, right? So even with single trees, this would be a nice functionality to have. There's BART. I tell you, the problem with, there's the one bad thing about BART is when you try to like improve it, it's really hard because it works so well, you just can't beat it. What's the point of doing it? That's pretty good, right? Look at BART, it's amazing. But there's the monotonic part. So that looks nice. The ideas I'm showing, of course, I'm showing you pictures with 2x's. All the ideas are the same with px's. Okay. So there's several examples on the paper. Here's just a 5-dimensional 5x's simulation. There's my BART burn-in. So let me just tell you what this. So this is looking at the root mean square estimation in the estimation of f. So it's a simulation, so we know the true f. It's not the actual forecast error. We're just comparing f hat to f because we know f is a simulation. And the idea is what we're going to do is just increase the level of the noise. Then the idea is that the more noise there is, there's less information in the data, so more value to the prior information. So if I give BART a ton of data, it doesn't, you don't have to tell me it's monotonic. I can see it's monotonic. Don't waste my time. And then with a lot of noise, it's like, it's hard to see, but then you tell BART it's monotonic. It goes, oh, thanks, that really helped me out. Okay. So see, sigma is just going up, 0.2, 0.5, 0.7, 0.1. So those are box plots of the root mean square in estimating the function across different simulations. So when sigma is small, so BART is on the left in each thing. So this is a set of simulations with the smallest sigma. This is the box plot of the root mean squares and estimating the function. This is BART. This is monotonic BART. They're the same. Jump to the biggest sigma. Here's my root mean square with BART. Here's my root mean square with monotonic BART. So if I up the noise, then that prior information pays off. Okay. So that's it. I'm going to stop monotonic BART there. There's some details. There's one, obviously there's some details I left out, but you got the gist of it. You got the idea. Let me skip ahead to, you got me going with that question because like, man, oh, that's the next thing anyway. Okay. The one that I wish I had, there's one example in the paper with real data where the noise level is super high. It's one of my finance examples. And the difference between the BART fit and the monotonic BART fit is huge. And how do I know it was monotonic? I asked my finance guys. I asked the subject matter experts, and they were confident it was monotonic. So I do have a nice example. We do have a nice example in the paper where you have real prior information in a real situation, and it really pays off because there's a high noise. Okay, so up to now, you have to say, oh, I know it's monotonic. Wait, that wasn't your question. Your question was, I want to find out from the data if it's monotonic. Okay, so we just switched it around. So now, before I could say, oh, if I knew it was monotonic, that would be useful prior information. Modulo, some technicalities, everything worked out fine. But now I want to say, gee, I'd like to know, I'd like to go through and say, okay, which variables are important and which variables are monotonic up, which variables are monotonic down. So we call that discovering monotonicity, as opposed to you knew it already. It's so funny when you do research. I always enjoyed this research because of the idea I'm about to show you is kind of goofy. So sometimes you enjoy research because you have like this just different idea. It's fun. And there's nothing wrong with that, right? But when you asked the question, I was like, oh, wait a minute. That research might be important. Maybe I better do it.
I think it's important, particularly for instance, if I'm holding stocks, right? If we can identify which stock is monotonic increasing or
Yeah.
decreasing, then we can take the measures to buy or sell the stocks. That could be very powerful for stock market, I think.
For lots of things. Even your biomedical things, which things make you worse. Anyway. Okay, so here's the crazy idea. We're going to write fx as a first pass. We'll just say we're going to write the function has a sum of a. So here I'm starting off with just a one. I only have one x to get some pictures and ideas, but the idea will immediately apply with many x's. Okay. Well, let me start off with just one x to get, because this is where it's kind of a little bit of a goofy idea, but it's going to work out. So I'm going to say this is kind of a math fact. You can always take any function. So again, x is just one variable. I can decompose any function that has a monotonic increasing part and a monotonic decreasing part. Okay, so the function's going up, that's the increasing one. If it's going down, then you turn off the increasing one, you need to turn on the decreasing one, and let it go down. So it's a fairly obvious fact. Okay, so that's what I have here. So obviously that's true in 1D. Okay, so here's the goofy idea. So I'm going to let, so I only have one x, but I'm going to estimate this f of x as f star. I put in x twice. I put in x, and then I put in x again. But the first x is constrained to be monotonic up, and the second x is constrained to be monotonic down. So it's like each x has an alter ego. It's a good Spock and bad Spock. In one time x comes in, but it can only do good. And next time x comes in and it can only do bad. So which x matters? That's the idea. So the correlation between my two x's is 1, for example. Okay, so that's my goofy idea that I claim solves your important practical issue. Okay. So how do I go to many? So what I'm going to do is just put in all my x's twice. But one time it's constrained to be up, one time it's constrained to be down. And then I can do variable selection. And I can tell you, if you don't come in as a up, then you're a down. If you don't come as a down, then you're an up. If you come in both, then you're not monotonic. Okay, that's the idea. Now I just have examples to show you that it actually works. Okay. I like this. Ed loves this. I love this too. Again, when you ask the question, I was like, oh, that's important. Yeah. Is that linear model? I always think about it, it's like, why would you ever do a linear model? Or it's so much better. But if I was a neural net guy, I would say, why would you ever do a linear model? I'm expert in Keras. Oh, you got to tune it. But I do it all the time. I'm really good at it. Boom, 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 boom. But then, people still like, oh, I can look at the coefficient. Oh, a positive coefficient, I can interpret that. So I want to give that back. Okay, so I'm fitting y equals x cubed. So this one is monotonic. And I have the BART fit and the M-BART fit. So I haven't done the discovery thing. So you can see the purple or magenta, I guess, that's BART. And you could say, oh, the squiggle, I don't like the squiggle. But if I know it's monotonic, then I can run M-BART, and that's the green. And now it looks fine. Okay. But over here, I did my discovery thing. So I put the x in twice. And then if I look at just changing the x that's allowed to increase, I get the blue is the part, the x constrained to be monotonic up. The red is the part constrained to be monotonic down. So you're supposed to look at this and go, oh, the monotonic up one does the job. I don't need the monotonic down one. It's monotonic. Now, it's just one picture. I can see it. But the idea is I can expand, I can apply that principle in a multivariate case. And then the green is the fit I got from running BART with both X's in and both constrained. So we're thinking as fitting F has the sum of a monotonic up piece and a monotonic down piece. So the green is fitting this model here. There's only one X, but I put it in twice. One's constrained up, one's constrained down. I just run that and I get the green. And the green looks better than BART. I said it was hard to beat BART. No, it's not. I just beat it. And when I put that X in twice, I didn't constrain it to be monotonic up. I didn't constrain it to be monotonic down. I got a better fit because it's smooth, because both of the monotonically constrained things are smooth. When I add smooth, I get smooth. And I can use this technology to investigate that issue you got me really excited about. Thank you. Okay. So we went crazy with this. We really had fun. I just increased the sample size. So easy this is. Well, now BART looks better, but it's still kind of squiggly, and BART looks great. But here I have, again, the blue part is if you can, it's just plotting the monotonic up part of the function. The red part is just plotting the monotonic down part of the function. So now I can discover that it's monotonic up because the monotonic down part doesn't matter. And the green part is the monotonic up plus the monotonic down, which is the same as the monotonic up, which is another way of saying it's monotonic up. Let's do one where it's not monotonic. So x squared. See how adventurous we are? We do x cubed, x squared. Anyway, here's x squared. So there's the magenta's BART. Wow, BART sucks. It's terrible. Why are we using BART? And then if I true M BART, obviously that's a disaster because I impose monotonicity. It's not monotonic. But if I do my discovery thing, then I fit the up part and I fit the down part. And, here's the up part, here's the down part, add them together, and it looks beautiful. This amused us no end. So the sine function is not monotonic. So if you fit, well, obviously I made the noise pretty small, the magenta, so I'm on the left-hand one. So BART obviously nails it with that noise level. Monotonic BART is the blue line, the straight blue line. Not a good idea. It's not, sine is not very monotonic. But look at the one on the right. So obviously the blue one is the monotonic up component. And obviously the red one is the monotonic down component. And you add them together and you get the sine. So suppose I didn't know, I was wondering if the sine was a monotonic function. And I didn't realize that the right way to answer that question is just plot it and look at it. I could figure it out automatically, right? By seeing that both the up and the down components are non-negligible. Neither one of them is small. Okay. So, I'm out of time. So I'm just going to assert. So I'm showing you 1D examples. This is a slide I would choose to end on. It's a little goofy. Let's end on something a little goofy. But let's make the heroic claim. then I can extend all these ideas to many x's just by putting each x in twice. One's constrained to be up, one's constrained to be down. If it's up and down comes in, it's not monotonic. If only its f up comes in, it's monotonic.
Does the MBART package do discovery BART?
No, so we've been dicking around this for a couple of years and we haven't published it. We haven't done. Okay, I'm done.
Any questions?
Thank you. I just want to say this is very helpful and useful. I'm really learning a lot about the monotonicity part. It's very useful. Yeah. Thank you so much.
Good.
Yeah, I was going to say, I mean, in the examples you showed, regular BART does so well, but like as you said earlier, with a lot of noise, this, you know,
It could make a big difference.
too. And then would you just like, do you just run this all the time now instead of BART? Just run monotonic BART up and down? Or there are other additional complexities that make that not so practical?
Okay, so the answer to that question is I should run it all the time. I don't because I didn't make the R package good enough that it's easy to do for me. So even I don't do it as much as I should. So one of the many things I need to do for the research is improve the R package. And that's a big part of our reality, right? Some people like to prove theorems. For me, I should be figuring out how to make this R package something that you can go in easily and find out what you ask me without having to work too hard, without having to think too hard. So I should be, but I'm not because I haven't made the R package nice and polished. And that's an important reality of all this stuff, right? Put out the software, you know, you get your paper published, that's one thing. What you really want is people to use it and feel like they learned something. And that involves the ideas, that involves my goofy examples, but it also involves writing a decent R package. That's why Rodney spent so much time on the.
Rob never wanted to release an R package. I had to convince him that it was a good idea. He never wanted to do it.
He's lying. It's a lie. Anyway, let's stop on. I'm done. Thank you.
All right. Oh, there's a question online. They say, is this a unique decomposition?
Oh, Ed thinks it is.
Oh, you're not on the microphone here.
You said. Rob says.
So Eddie, did you say Eddie said it? So Eddie George claims this is a unique decomposition.
He's not right. Just add 5 and subtract it from F up and F down.
No, but I think Rob said up to a constant or something, didn't you earlier? No, but he's saying not up to a constant. So we should thank Rob. He's going to get in his electric car, hopefully, and go to O'Hare and fly home. So Rob, are you gonna have lunch with us or no? Are you having lunch with us or you taking up? All right, so he's. Ongoing basis, I did All right, so let's thank Rob, and I'm going to stop recording. All right, we're going to pick up on the schedule where we left off. I'm going to talk about a biostatistical application here, but it's I think it's very relatable, even for people not interested in biostatistics. Well, let's see how this goes. All right, so this is some joint work that I did with some people here. We call it novel pediatric height outlier detection for electronic health records, machine learning with monotonic BART. This research was supported by the Children's Wisconsin Foundation through the support of the Lambs Fund and the Abraham Family Fund. The motivation, clinical application in chronically ill children, yada, yada, yada. Okay. So this data is from the electronic health records of a large children's healthcare system. Chronically ill children are often at high risk for malnutrition. Typically, this is assessed by comparison to CDC growth chart benchmarks. CDC inputs are age, gender, height, and weight. Age and gender are extremely reliable. However, height and weight are prone to outliers, and there is practically no quality control for these measures. In other words, the ground truth of height outliers is largely unknown. There are about an order of magnitude more height outliers than weight outliers per measurement. So about 3% is the estimate of height outliers and about 0.2% for weight. So weight is relatively more reliable. Determining malnourishment requires height outlier detection. Furthermore, this method should be robust to weight outliers that are harder to identify, but like I said, less prevalent. So there's been a fair amount of work in this area, but it's how do I want to say this? Generally, the methods proposed are either too simplistic or too complex to implement, which I can explain more as we get into this. So this is a CDC growth chart. So I showed this yesterday. So on the x-axis are age for girls, and on the on the y-axis are heights in centimeters. And the 50th percentile is the dark line, and it's the center of the distribution. And then there's various cutoffs that can indicate malnutrition or some sort of growth challenge. Yeah, and so there's some percentiles. Okay, so like I said yesterday, the CDC and WHO have developed growth charts for child development, height by age, weight by age, body mass index by age, and weight by height. We're going to focus on height only. These are age in months for girls 2 to 17 years old. Actually, it's not just girls. We have boys and girls. The CDC uses this LMS method that uses natural cubic splines. It draws those nice curves that we just saw. They're very smooth. These parameters are estimated by penalized maximum likelihood. So there's a series of L's. That's the Box-Cox power transformation. There's a series of M's. Those are the means. And there's a series of S's. Those are the coefficients of variation. So, so if L is 0, they look like this. So you take logs. If it's not 0, so it's just the typical Box-Cox thing. Now, the CDC and WHO guidelines say values of ZT that are less than 6 or greater than 6 are outliers. But that would only catch the most extreme outliers, right? I mean, so that's pretty simplistic methodology. So regardless of the exact cutoff, you could, I'm calling this method, or some people call this method standard deviation scores, SDS, right? So in other words, people are using the growth charts in 2 ways. They're using it to monitor malnutrition, and they're also using it at the same time, they're using the same growth charts to determine what's an outlier. So that's called SDS. But it seems to me that's way too simplistic. Oh, so this is just what Rob was just talking about, monotonic trees. So if we have two trees like this, you have these regions, and they have these monotonic relationships, right? So mu 12 here has to be less than mu 16, and mu 16 has to be less than mu 17. Similarly, over here, mu 24 has to be less than mu 25 and less than mu 23, right? So as long as the trees are monotonic, then the ensemble of trees will be monotonic. All right, so Rob already said this. I'm just going to skip this slide. Here's something he didn't say. What is the prior for the leaves? Well, for BART, it looks like this. So the leaf values given the tree are normal, 0, and with some variance. But if we consider the simplest case of two monotonic leaves, they rely on these results by Azzolini that look like this. Okay, so there's this joint distribution like so. With this mean and this variance, and subject to this constraint, where this c squared is approximately 1.47. That comes from the geometry of the problem or the calculus. I mean, you can derive this quantity. You'll see if you look at Azzolina. Oh, so what you want is equivalent to skew normal marginals that are like so. So a variance of mu1 variance equals the variance of mu2 equals that, right? Well, in order to get that, you end up with priors that look like this. The prior for mu1 would look like that. So you've got this piece that comes from the standard normal PDF, and you've got this piece that comes from the standard normal CDF. And similarly, mu2 is like that, right? And so mu2 is greater than mu1. Oh, and the expectation of mu1 looks like this, and the expectation of mu2 looks like that. Here's something that Rob also skipped. So in regular BART, we have these two parameters for the tree penalty, alpha and beta, and in prior probability, 5% of the time you'll have a tree with just a root, 2 leaves with 55%, et cetera, right? Well, the way, due to the sampling scheme of MBART, that doesn't exactly work. So actually, the settings are radically different. However, due to the complex way that MBART is sampled, like Rob kept saying how easy it was, which was making me laugh, because it's actually extremely complicated. But actually, these settings turn out to be about the same as these. So you can look in the paper to see how that's done. It's much more difficult, I think, than he was giving on. All right, but you don't need to know any of that. So there is a nice software package. I showed that yesterday. I can show it again where that software package is that does monotonic BART. It doesn't do the discovery BART that he was talking about. It just does plain monotonic BART. Okay, so here's something. A nice property of monotonicity. It's a robust to outliers. Why am I saying that? Well, this F function, if there's an outlier, it just can't go up for that outlier and back down to the rest of the data. And BART will do that. So if you have a big outlier here, BART will hedge up. And you don't want that, right? So monotonic BART does not do that. It just goes, it pays no mind to that outlier. So that's nice. So let's assume that our F function here is for monotonic BART. So we have population predictions of the form like so. One thing I didn't say is these kids typically don't just have one measurement, they have a series of measurements. That is totally ignored in the CDC's method of finding outliers, but we're going to take advantage of that, right? Because if you just see the kid once, who cares? If you never see him again, well, fine, you know, whatever happened to them, it doesn't matter, right? So you need a series of these, and these kids that I'm talking about are chronically ill. They are seen a lot, so they have lots of height and weight measurements. Anyways, we have these population predictions like so, and so recall mu is just a constant, roughly centering the population. But these expectations are biased except for the average child, right? So these, for a child on the average glide path, these are perfect. Well, that's only good for the average child, right? And most children are, well, some children are average, but a good proportion are either up or down, right? So we need to adjust these up or down for a given subject. So, so what I did was I took the median of their values and I subtracted off the population median, the population expectation, and I say median rather than mean to be robust to outliers, because the whole point of this is we know they're outliers, right? And we want to get rid of them. So then we have these personalized predictions like so. So I call them Yij tilde, and you have this personalized M like so. And then we just look at the relative error of these, and like so. So we take the truth minus these personalized predictions divided by the personalized prediction. And then we define the outliers like so. The absolute value greater than delta, where you can pick these delta from an ROC curve. And the discriminating performance of the method is assessed by area under the ROC. All right, so let's get back to this real data example. We had two cohorts of chronically ill children, 2 to 8 years old. These kids were measured at least every 120 days on average, and they were followed for at least 2 years. The training cohort was 1,376 kids, and the height outliers were unknown. We didn't know who had an outlier, who didn't, right? So that's almost 40,000 measurements. So on average, each kid was measured about almost 29 times. So these kids are seen a lot. We also had what we called the validation cohort. We had 300 children, about 7,000 measurements, and close to the same number. They had about 23 measurements on average. Here we manually reviewed them to determine height outliers. However, this is a fallible method, right? We couldn't go and remeasure the heights of these kids because this was retrospective data. But they did their best. We had a panel of experts that dietitians, MDs, et cetera, that looked at these series and said, aha, that's an outlier, that's not, et cetera. But we couldn't do that for all of these kids, right? There's just too many kids, right? So 300 was already taxing our abilities. So heights in the training cohort, we fit those with MBART. And we had access to age, gender, race, ethnicity, and weight. So like I was saying, we conducted outlier detection manually in the validation cohort, and the area under the ROC curve was excellent, I would say, 84%. So if you use the height SDS group growth chart method, regardless of your cutoff, the area is only about 78%. Actually, I was surprised it was that good. I mean, so it wasn't as terrible as I thought, but
but obviously our method is better, right? Otherwise, I wouldn't be here talking about it. But picking the exact cutoff, it wasn't clear to where exactly to put the cutoff is. You could kind of see several places, but we just tried 2 different cutoffs, and the results are pretty similar. All right, so let's see. Let's go through a quick summary here. Let's see. There was the majority of the kids were male. The majority were white, although at this particular institution, a large group were minorities, right? About 40-some%. In the training group, obviously, we don't know who had outliers, but in the validation group, there were 101 children with outliers. So that seems really high, but remember, these kids are measured 23 times each, right? So there's thousands, and at a 3% error rate, you can see that, looking at any particular kid, that dramatically increases their chance of having an outlier, like about 32%, right? Let's see, what else can I tell you here? Oh, so the R squared here was about 82%, which was pretty good, I thought. And of course, it goes down a little bit in the validation group, but it's still pretty high, 75%, which is a pretty high R squared, higher than most data that I've ever looked at. So it was pretty decent. Oh, and here's what the ROC curve looks like. You can see here's our method, and like where you pick the cutoff is not clear, but like we think it's somewhere in this region, right? But you can see that our method dominates the SDS method, right? Except for like one or 2 points, right? All right, so I have some 2x2 tables here, but I just wanted to go over some of these stats. So sensitivity, or like they call it in the machine learning literature, they call it recall, about 71%. Specificity at this, so this is what we call the aggressive cutoff. Specificity about 0.8. That's pretty good. P positive predictive value, or in the machine learning literature, they call this precision. It is about 60%. That's not great. But the negative predictive value is really high, 0.856. So this is an interesting thing. We've been talking a little bit about machine learning. Machine learning people only look at these 2 numbers, generally. They almost never look at these 2. However, I think ignoring those 2 is a big mistake. I don't know. That's my opinion. So there's more slides here on different cutoffs. I'm just gonna skip ahead here. Let's see here. Oh, and I also mentioned, so there's this thing called targeted smoothing BART. So as Rob was saying, even monotonic BART is smoother than regular BART, but it's not completely smooth, right? So, but there is a method called targeted smoothing BART that is smooth. It talked about in this paper. I tried that. The results are pretty much the same as monotonic BART, but I just for comparison, it is really slow to fit though, because each one of those leaves are Gaussian processes, and that is slow. So it's like you've got the worst of both worlds there. You've got BART, which is already, it's not a super slow method, but it takes a little bit of time. And then you add Gaussian processes, and it just makes it crazy slow. I also looked at, just females. There were the minority here. Just non-whites, there were the minority, and the results are pretty similar. So here, I just wanted to go look at some of these kids and show you some examples. So here are some true positives. So on the left side here, this row is one kid and this row is another kid. So you can see here I have height on the y-axis, and on the x-axis we have age, and in this row it's weight on the x-axis. So here I've overlaid in dashes the growth chart, but I mean, anybody could have told you that was an outlier, right? but they weren't all this obvious, right? So like here, I can show you below. Here's an example. So that's the outlier there. Can you see that? It's subtle, right? On both the weight chart and on the height chart, it's. But anyways, we picked that up. We picked that up, and they said it was a real outlier, right? Manually reviewed, it's a real outlier. This methodology also picks it up. All right, so how about some false positives? Okay, so here are cases where the manual review is saying there's no outlier, but we pick up something. So here you can see this one. Oh, I should have said this. So the black dots are observed and the blue dots are the predictions, right? And you can see here that we're saying this one's an outlier, but notice it's the only one out of all of these that are an outlier. So it's like very close to the limit. So we're saying that one is an outlier. That's probably, I mean, there's something going on with this kid though, or I don't know, maybe not. I don't know. So the manual review said no. So I guess we got to go with that. And then same thing over here, right? It doesn't seem to be that extreme, right, compared to the others. Although it is interesting that that one value is on the heaviest. So it was like on the heaviest value, right? Here's another one where I think the manual review is not right. So here we're detecting this is an outlier, and they're saying no, right? That looks like an outlier, but hey, who knows the truth here? Okay, false negatives. So here's a case where they're saying it's an outlier and we're saying it's not. Is that right? Let me think here. I haven't looked at this one in a while, so let's see. So there's the outlier. And our prediction is here. That looks like an outlier. Let's see. I must not be reading this graph right. Here, let's go to the next one. Oh, that's it. This is the last one. So let's see. I don't know. I have to think about that one at the break. Okay, so we have this new outlier detection methodology based on monotonic BART. It's automated, so you could do this. You could do this in the EMR, right? You'd have to check. You'd have to independently validate it, of course, but that's not easy to do, right? So I think this is one of the problems with the EMR. It's nobody's job to fix bad data, right? Things go in, it's sort of like a cash register. It's for payments, and it's nobody's job to go back and fix stuff that's wrong. So I think this bullet is probably the most important thing. So there's some, I showed you the SDS method, which is about the simplest one. There are some more complicated ones, but most of the methods have these multiple rules, and you have to simultaneously tune the cutoffs. And actually, that is very hard to do. The fan paper was based on a big data set from the UK. We tried it on our data, and it just didn't work. I don't know what exactly the problem was. So we tried to retune it on our data, but there's like there's like 3 or 4 rules, and you had to simultaneously tune it. And we're like, well, this is too complicated. Ours, we have a very simple single rule, right? Oh, and I already said this one. So it's nobody's job to go back and fix these, but for a research database, we can go and say, we can flag them and say, hey, don't use that value. And that's exactly what we did. All right. Any questions about this before I move on to the next talk? All right. So there's no questions online either. So, okay, so I'm going to move into the last, well, not the last talk, the next talk. All right, so now I want to talk about BART and time to event outcomes. So I wrote this abstract and I'm going to spend a couple minutes on it because I think this is really important. And it's often misunderstood, I think. So the deficiencies of parametric time to event survival analysis led to semi-parametric methods. So that occurred back in the 70s. However, ensembles were only discovered in 1997, right? So that, along with technical advances like Moore's law, are leading to another transition to largely non-parametric methods today. So what do you base a new non-parametric method of survival on? Well, we picked BART. I mean, certainly you can do it in other ways, and people have done that, but we already have this nice tool for continuous outcomes, for dichotomous outcomes. So we're like, okay, let's extend it to BART, and we're not the only one. Several other people have been working on this also. BART has a lot of good things going for it. It's relatively flexible. It's a non-parametric approach with no precarious parametric or semi-parametric assumptions such as linearity or proportionality. Due to its Bayesian non-parametric underpinnings, BART can be naturally extended to interpretable functions as targets of inference, along with their measures of uncertainty, for example, the survival function. Okay, so I mentioned, semi-parametric models like Cox were a godsend, in the 70s. That's a little bit before my time, but when I came along in the 80s and 90s, this is how we did things, right? So I'm not saying there's anything wrong with the method. Well, I am going to say that, but I mean, at the time, it was the best we had, right? And I think it was really really well done. I mean, one of the most cited papers of all time, right? So let's just see. So I think there's some similarities to the Cox model to what our first adaptation to survival analysis with BART. So one of the similarities is, besides the notation, right? So we have time, time, whether that's an event or not. So if delta is 0, it's censoring, and 1 if it's an event. And then we have this grid of times, right? So these distinct ordered times, you create this time grid, right? So you have the first interval, 0 to time, the first time, et cetera, all the way up to the last time, right? That's going to be similar. Here's some things that are not going to be similar. So here, the hazard is some function of time, and then this multiplier, which I call proportionality. Notice that assumes this is linear, right? Also notice this is not a function of time. That's what's called proportionality, right? Those are both very strong assumptions. Anyways, this is the Cox method creates what's called the partial likelihood. So what you do is you ignore this thing. You just condition on that. That's why it's called the partial likelihood. But the point is, here's something interesting, right? So by construction, you create a survival function like so. So it's e to the cumulative hazard. So that's going to be a similarity. We're not going to directly model the survival function, but we're going to create it by construction. Okay. All right, so here we go. So like I said, we have this grid of times, and we're going to use something called the discrete time approach. What does the discrete time approach do? Well, it creates indicators in each one of these intervals. You know, did you have an event or not? So, so we have these indicators. Y, given the probability, is Bernoulli, all the way up to the last time point you're observed. So it's going to be in the first interval, if you didn't have an event, you're a 0. In the second interval, if you didn't have an event, you're a 0. In the third interval, if you had an event, okay, you're a 1, and then you have no fourth interval because you're done, right? Once you hit an endpoint, you're out, right? So that's what these indicators look like. And we're going to model these probabilities like so, as a function of time and x. And now notice that x can also be a function of time, but I'm not going to talk about that any further today, but that is certainly a possibility. Anyway, so now we get a real likelihood, right? We don't have a partial likelihood. We have a real likelihood. And we can construct survival like so. It's a very simple construction from the P's. It looks like that. So we have a discrete time intensity model. It turns out it's also can be a longitudinal binary regression model. And guess what? We're going to use BART. It didn't say it on that page, but this is all pretty much the same. The only difference is right here, right? So we have this model here. And by the way, the discrete time approach has been around for decades, right? But how do you do this, right? So they tried all kinds of things, like one of the most common ways was they would model T as a spline. But you know, how well did that work? I don't know. I don't know, right? You know, it really depended on how good you were with splines, which is one thing I hated about splines. They take a lot of work, and yeah, it was messy. So my idea was, let's replace that with BART. So that's what we did. So now here we've got a probit. We've got the normal CDF is mu plus this f function of time and x, and we say f is a prior with BART, and we only use 50 trees here because what happens is since you're creating all these indicators, you get a big data set, right? You get k times your normal size data set. So you want to save a little bit of computational speed. Plus, there's been a lot of work saying that 50 trees is probably good enough for most things. Okay, and this mu hat looks like this. It's the inverse CDF of y bar, which is y bar is just the mean of all those indicators. And again, just like I showed before, you're getting the survival function by construction. Okay, so we can estimate our function here by averaging over the posterior, but nobody really cares about the f function, frankly. Most of the focus is on the survival function. So this is our estimator of that. And of course, we can create credible intervals by taking the quantiles from this distribution of the S of M's, right? Okay, so I talked a lot about marginal effects yesterday. And again, we could do the marginal effects of the f function, but like I said, nobody cares about the f function. So what we're going to do is we're going to use Friedman's trick, and instead of the f function, we're going to use the s function. So I have all the steps on this slide, but basically, all I've done here on this slide is I've just replaced the f's with an s, right? So now we can get marginal effects of the survival function. Now this is assuming these are independent, but we know how to fix that now, right? Okay. And a big part of working with these models, like a Cox model, is you want to have relative risks, right? Well, we can do that. So we have relative risks. Now here, though, they may be a function of time, right? So time is here. So you have some X settings for the numerator. You have some X settings for the denominator. And you may also have some XCs that you don't care about, right? So you could be marginalizing those out. Well, so you could take the relative risk like so. For the mth step of the mth draw of the MCMC, you formulate your numerator and you divide by your denominator. That's your relative risk. That just looks like this, right? And then you can, so I'm assuming that you're going to marginalize over these, right? So how do you do that? Well, we just use the Friedman function trick, right? Like so. And then now, if you want to assume proportionality, you can also take those estimates here, right? And you could average them over the time grid, right? But you better be careful that it's relatively flat, right? And I must say that, you know, in many cases it's not. All right, so this is just a little bit about the package. So serve.bart is in the BART package and in the BART3 package. I think I'm going to skip over this, but I might do some hands-on. Let's move ahead here. Let's see. Well, I think there is one important point that I should talk about. All right, let's go through the slides. Okay, so here we have the serve.bart function, and you can see now we have X train, and now we have times and delta rather than Y, right? Because now we need those. The number of trees are 50. And so because we're doing it based on a dichotomous BART, we're going to thin, right? Typically, you don't do that with continuous BART. You don't. I mean, you could thin, but often we don't. All right, so that's with no multi-threading. With multi-threading, there's mc.serve_bart, and you just have to tell it the number of cores and the seed, but it's basically the same thing. All right, so this times vector that you're inputting, we're assuming that you've already created the k distinct times, distinct values, right? All right, so from this post object is of type serve_bart. It's effectively a list. So it includes matrices like post, prob, train, also the survival function. It has a lot of things in it. All right, so so one thing I didn't say was, let's see here, and I'm going to come to that. So typically in BART, we have a training data set and a testing data set. But notice here I'm saying X test is X train. Why am I doing that? Well, so like I said, we're expanding we're expanding these the data set on this grid of times, right? So you have to expand X train in a similar way. However, when you want to calculate the survival function, you need everybody to be on the same grid, right? Whether they died or not after the third interval, Who cares? You want their whole survival function, right? So that's what we're doing here. So we're passing the training data, but we're going to complete the grid. So you can see down here now that I have complete grids, and I can estimate the survival function over the whole grid, right? But I can't do it on the training, right? Because the training is only expanded up as long as you survive. So we use that trick. But now, be careful though. Now the testing data set is not really a different data set, right? But in survival analysis, often, well, I shouldn't say often. I don't know. That's just the way it is. Now you can still use the predict function to predict for some other data set. Here on this slide, I'm showing there's this function that's called, it's a helper function, and it helps you by doing the expansion for you, right? So it expands the X train, and so for example, calling this function, you create this pre-object. This pre-object, for example, has two, let's say two. So here I'm just supplying X train. I'm not supplying X test. So it creates a TX train and a Y train, and notice that that these X's are expanded, right? So from the first patient, we have all of these rows, and you can see that we have all of these rows in Y, and the last one is their delta, right? So if the last one is a censoring, this is a 0. If it's a failure, it's a 1, etc. Oh, and for test, everybody gets the full grid, right? Here, it only goes up to your last interval. Here it goes throughout for the whole grid. Okay, so like I said, you can also predict. So here you can supply here. You can actually supply another testing data set if you want, or you can do it for the TX test that you got from pre, right? All right, let's look at an example. All right, so there's this famous example in the survival package that we also provide in the BART package. It's the advanced lung cancer prognosis. They surveyed 228 advanced lung cancer patients. The study focused on prognostic variables. There's age, gender, Karnofsky performance score as rated by a physician. And we're going to compare males to females. So this is in the BART package. It looks like this. And I'm going to run this right now. All right, so this is in the demo directory, as we showed you how to find that yesterday. I can remind you if you guys don't remember. All right, I'm going to start it off, and then I'm going to talk a little bit about it. Let's make sure it's running. Yep, it's running. So let's see, what did I do here? So I loaded the lung data set. I have a table of some of the values here. What should I say here? Oh, it's done already. See, so that was pretty quick. But it's only 228 patients. So what I did was the times I think are in days. So I made it to weeks. See that? Now, let's see here. So if you look at, so this data frame, I have sex, age, Karnofsky score, and then I also have institution, right? I think some of these are missing. So let's see if we can see that. here, I'll just do, oops. No, they're not missing. Okay, well, that's interesting. Maybe I fixed that above. Let's see. Yes, I did here. Yes, yeah, I fixed it here, but my point was going to be you don't have to do that. Okay. BART uses a cold decking approach to imputation. I don't know that I have a slide about this, but I can go into it if there are any questions. So it's and it also does multiple imputation. So if you're not using Dart and you're running multiple chains, each chain gets its own imputation. All right, what else can I tell you by looking at this? Oh, another thing I can tell you is we used the new FPD functions. So what I'm showing you in this graph here is I have the marginal effect of females versus males. And how did I get that? I got it like so. So here I provided, what did I provide? So let's see. So see, I created this object called x.test from tx.test, but here I'm only taking the first two columns. Well, why am I taking only the first two columns? Let's see. Or is that first two rows? Oh, that's the first two rows. I lied. Yeah, why am I taking only the first two rows? There's only two sexes, right? 1 and 2. So here, but okay, I'm explaining this badly. Let me see. Let me show you what x-test is. All right, x-test looks like this. So it only has 2 rows, but it has the same number of columns as xtrain, right? It has all of these things, but also it has the times column. So the first column is time and everything else is moved over 1. Because that's what the FPD needs. It needs to know that we're doing these two. Well, yeah. Actually, I'm only, yeah, okay, sorry. So it's actually doing only this one, right? Because you see, I'm saying S is 2, so it's only doing sex, right? But the FPD function is smart enough to know you want to do that on a grid, right? So if I just did males and females, this wouldn't work, right? I also need it on the same grid of times as everything else, right? So it's actually doing a 2-dimensional partial dependence function here. Time and then the males and females. That's what I want to tell you. But you can do it pretty easy. I mean, frankly, that's it. You need these 3 lines, right? Okay. Any questions about that on that before I move on? Okay.
You mentioned previously, for one subject, you need to expand into multiple observations for given different event type.
Yeah.
Before, I think we call the .bar.
Yeah, it does that automatically. So, yeah, so serve.bar does it automatically, and mc.serve.bar. But I mean, I just showed you what the internal function does, so you can see what's happening. But yeah, you don't. I mean, you could call it if needed, and there are situations where you might need to, but this is not one of them. Oh, and there was another example I wanted to show you on the relative risk. So I'm just going to start that. Actually, let's see here. Actually, I don't need to do the fit again because I've already got it. I just need to run this block. Let's see. So here I'm going to calculate the relative risk. All right, so it's running. Oh, it's done. Prediction is done. I'm going to plot it. So that's what the relative risk looks like between males and females. So you can see the risk. So like if I just assume proportionality and just average all of those, it's about a 2 times relative risk for males than females. And I think I understand this. So this data is a little bit old. It's from the 70s, and at that time, typically lung cancer came from smoking, and men smoked more. Luckily, the ladies have closed the gap, and nowadays they smoke just as much as men. so there's no more gender disparity. Now men and women die just as quickly. But at this time, men died faster, and you can see that here I'm graphing the proportional, the non-proportional value and the proportional value. And you see they're pretty close, right? So it's about 2, but it's there's a little bit of a trend over time, but I don't know. It's just above 2 to just below 2. 2 seems a reasonable estimate, and so that's what that example does. Okay. Any questions about that? All right. All right. So let's go back to our presentation. Oh, and convergent diagnostics are a little bit tricky, but it's very similar to doing for the dichotomous, and all this is explained in the JSS paper. So I'm not gonna talk about that today. But there is an example in the demo where you can play around with it. All right. So now I'm going to return to the diabetes example. And since I just talked about it, I'm going to skip this slide. Let's skip this one. Okay. So how do you analyze recurrent events? Recurrent events are a little bit tricky because in survival, once you reach an event, you can't have another one, right? Once you reach an event, you're done, right? Well, that's not true with recurrent events. So there is some sort of dependence between them, right? Like if you have one event, for example, in diabetes, for hospitalizations, it turns out you're far more likely to have another. All right, so we have data like this. So we have a death time and we have a bunch of hospital times. Now this may be 0, but let's say that, you can have 0 or more hospitalizations, and then you have these time-dependent X's, right? So the X's change all the time. So we create a grid again, and we create this. It's the same grid for both death and times. And now again, we have these Bernoullis, but it's a little bit different than before. Like I said, so one person is not just one just at the end. They could have several ones, right? But we're modeling the probability very similarly. We have a similar likelihood. However, in recurrent events, the focus isn't so much on survival because, well, I mean, you could also look at survival, but I mean, the focus is on the recurrent events rather than the terminal event, right? So people focus on the cumulative incidence, like so, and if you do this integration, you actually you get something remarkably simple. It's just the sum of the probabilities. right? So now we have a discrete time intensity model. It's a longitudinal binary bar, just like before, more or less. Except for I didn't tell you something. Well, I did say it. They're dependent, right? So if they're independent, what I showed you is right. However, they're not, right? These are not independent. We assume they're conditionally dependent given some x's and the event history, which we summarize by NI and VT, okay? So NI is the number of events prior to the current time, and yeah, number of events prior to the current time, and something called the sojourn time, which is the time from the last event, right? And if you never had an event, it's just T, right? So you start out like so, like with a 0 at time 0, right? There's no events, etc. Anyways, so if you condition on that, then they are exchangeable, or roughly so. So we've got the sojourn time, we have the number of previous events, and X. And that's what you need. All right, so this is the same slide I showed before, but keep in mind, we want to be able to identify these people before they have all the hospital events, right? If we just wait till they have all the hospital events, it's you know, first of all, they're going to consume a lot of services, right? This 10% of the population is consuming 63% of the services. I think I said all of this. Yeah, so one thing I didn't talk about when I got to this slide before, so we have these risk agonists: insulin treatment, peripheral vascular disease, and the number of previous admissions. I'm not talking about calcium because we divided the data set into 2 data sets, and we ran the search on one data set, and that calcium came up. However, when we ran on the other data set, calcium didn't seem to be as important. Also, like I said, the physicians weren't real crazy about calcium. They're like, yeah, okay, but you know, so they didn't really have a good reason to include calcium. So we dropped calcium, but we included insulin. And insulin, I think, was kind of in the same boat. It was like borderline in one, but they wanted insulin in there, so I put it in there. But whether insulin really matters or not, I'm not 100% sure. It certainly divides the diabetics into groups, though, right? So some diabetics can get by without insulin, and some diabetics need insulin. So obviously, that's, you know, once you get to taking insulin, you're pretty much on it for life. Very few people can stop taking insulin. Type 1 diabetics never can, and type 2 diabetics, usually once they get on it, they have to stay on it. This is the same slide I had before. None of these things seem to matter greatly, interestingly, so I'm not going to talk about them anymore. But let's talk about insulin and PVD. So insulin, the relative intensity is about 2.39 with a credible interval like so, 1.5 to 3.2. And PVD is almost a 3, 2 to 3.89. So that's almost a 3. That's a big, that's huge, in my opinion. I mean, 2 is not bad either, but it's a third more. Okay, but now how do you do? So how do you make the partial dependence functions out of this? So I wanted to create these risk profiles. So I created 3 risk profiles: low, medium, and high. So in medium risk, they were just on insulin and not PVD. And in high, they were on insulin and had PVD. And low, they had neither, right? And then, you know, how do you handle this previous number of admissions, right? So I had to make scenarios like this, right? So in low, they never had an admission. In medium, they had one at 2 years, and they never had another one. And high, they had one at 12 months, a second at 24 months, a third one at 36 months, and fourth one at 48 months. Okay. So that kind of runs the gamut, right? So what I'm doing is I train the model on the data, and now I want to make inference on the disease process as a consequence of my model, right? So now I'm going to use all that richness that's in the model, and I'm going to use that to my advantage. So this is what the risk profiles look like. I don't find this one particularly all that exciting. This is the one. One's my favorite. So if we look at the relative risks, so this is the medium versus low. You can see that this is about 2.5, right? So if you're in the medium group, your risk is about 2.5 times that you're going to have an admission. But notice what happens here. So this is where they had one previous admission, but notice how it decays. So what that tells me is, so it takes a while, but notice it decays back down to 2.5, right? So what that's saying to me is the sojourn time matters. Like, it's not just that you had a hospital admission, but it's like how recently you had an admission, right? So the more recent, the higher the risk, but eventually that degrades, right? Similarly, for high versus low, you get the same sort of sawtooth pattern, right? So here's the first event. You can see that it's up to there. And these are really high, right? This is like over 7. I mean, that's an enormous risk, but it drops down to about 7, right? Yeah, so this is 7. This is over 7. It drops down to back by 2 years. Again, you had an event, it pops up well above 7. It degrades a little bit, not as much as before, because you've had 2 rather than 1. So that seems to be worse. And then again, you get to your third event, and then it's a big increase, right? Almost up to like 9, and then a little bit drop. So once you get to this level, it doesn't decay much, right? You're at a high level from then on. So that's how that's how I analyze this study. Oh, and keep in mind this is for the population, right? You can also do this for the predictions, but you can see when you get to the predictions, the intervals are super wide, right? So individual level predictions are really wide. So identifying these people maybe is not as easy as we thought, right? But again, the average risk is super high, right? Okay, so some diabetes patients are at high risk. PVD, prescribed insulin, maybe. Recent hospital admission, that's definitely the case. And or several previous admissions, definitely. So there's some health policy implications here. Diabetic patients, healthcare post-discharge should be carefully orchestrated to ensure the delivery of quality clinical care, which maximizes healthy outcomes while preventing adverse events and costly, unnecessary hospital admissions. So in the BART package, I have the 20% random sample of this data set because on CRAN, they only give you so much space. But in the BART3 package on GitHub, where they give you a lot more space, I have the whole data set. So any questions on that before I move on? I just need to check the outline to see how we're doing on time here. Let's see. You can also do this with competing risks. It's the same issue. There was semi-parametric methods, but no real good non-parametric methods for competing risk. Well, I shouldn't say. Okay, I'm exaggerating, but I mean, there were a few methods that were competing risks that were non-parametric. So, so how did we do this? Well, the way we did this was we said, okay, well, first of all, you could have no event. You could have the event of interest or a competing event, right? That's what a 2 is. And if you do that, you can do the same trick, the discrete time trick, right? So now you have indicators for either event, and then you have an indicator that's just for the type 2 event. So it's a simple extension. Well, it only took us like a year to think about it. I mean, I knew it would work, but I didn't know exactly how, and so we figured that out. So, but what gets complicated is how you calculate survival now. It's a bit more complicated. Well, actually, survival is easy, but how you calculate the cumulative incidence is a little bit more complicated. So you get these. So this is the cumulative incidence for event 1 of type 1. You can see it's sort of a complicated function like that. For all the other events, it's like that. The good news is it doesn't matter how complicated the function is. As long as we can calculate it, we get the uncertainty for free from the +2. Oh, and there's another way to do this. I'm not going to get into it, but I mean, both methods seem to be pretty much equivalent. But I mean, that's not going to be the case, I suppose, for all data sets. But all the data sets that we tried, it was pretty much the same. And we did a lot of simulations. Oh, and you could also extend this to more than 2 causes. I'm just going to skip that. Oh, okay. But here's a famous data set. This also comes from the survival package. All right, so Mayo Clinic has a liver transplant waiting list from 90 to 99. During this period, the liver organ allocation policy was very flawed. Donor livers from subjects with blood type O can be transplanted into patients with A, B, AB, or O blood types, whereas an A, B, AB liver can only be used by a recipient of the same type, right? So type O subjects on the waiting list were at a huge disadvantage, right? They had a large pool of competitors for their type O donor livers. But current policies have evolved, and they depend on each individual patient's risk and needs, which are assessed and updated regularly. However, I just want to highlight that it's still pretty rough because they don't have enough donor livers to go around, right? So it's a little bit better for type O patients now, but it's still bad, right? So this is the transplant data set. There's a non-parametric method that doesn't do regression called Olin-Johansson estimates. And in this case, we don't really have a regression, right? It's just type O versus, it's just type O versus other types, right? So if you look at this, you can see that type O, let's see, how does this go? Transplant. So let's see, type O survive. All right, so if you look at this with this Olin-Johansson, you get a cumulative incidence function looks like that. If we do it with BART, we get the blue line. And of course, we get credible intervals. I mean, I guess you could probably do that with Olin-Johansson. I don't know how that works exactly, but anyways. So So it's pretty, you get pretty similar results. All right. So I'm going to move on to the next part of the talk. Well, first, any questions about this part?
The computing risk is also difficult. Difficult there is how to model the correlation structure between the risk of
So with the conditional probability, this is how you do it. Now, if you're going to take a different approach, what people do, I think, and this is what we're working on too, is you have some multivariate distribution. You say, okay, time to death from cardiovascular disease has this mean in this variance. Cancer has this mean in this variance and this correlation with the other one, et cetera. So that's how they do it when they're not looking at conditional probability. When you're doing conditional probability, this is the way you do it, right? But yes, there are other approaches, non-parametric approaches, but I think ours is better. Well, we compared so our big competitor is random forests. So we compared with random forests, but I think we beat them, as I recall. Yeah, I'd have to look in the paper. Let's see. I'm pretty sure we beat random forests. I think trying to remember what the issue with random forests. Oh, well, one of the issues with random forests is they don't naturally produce credible intervals, like like we have here. They don't naturally do that. Now, there is a way to do it, but it's complicated and typically, well, I shouldn't say typically. As far as I know, there's no R software. Now there's a Python package to do it, but I don't know. I don't use Python, so plus I use BART. So, but yeah, I think we beat random forests, but there's always new things coming out with random forests too. So they're getting better all the time. But currently, as I understand it, we beat them. Okay. Any other questions? All right, so we've got about an hour before our break. So I'm going to talk about non-parametric failure time. So this is an article that just came out in March and that we were working on for a long time, of about 4 years. And this research was sponsored by the Office of Naval Research. Yeah, so just hot off the presses. I'm just going to skip the outline. So what is this motivated by? Well, so we're just talking about liver transplants. Well, for blood and bone marrow cancers, they have these hematopoietic stem cell transplants, right? So Rob was saying, like, his dad was one of the articles we cited. His dad was involved in the group that discovered stem cells. Well, it turns out, what are stem cells good for? And they're good for transplanting. They're a good therapy for transplanting. They're good therapy for blood and bone marrow cancers. What they do is they ablate your bone marrow so you don't have any, because that's where those evil cells are coming from. And then they transplant new bone marrow for you through stem cells. One of the questions was, how do you pick a good donor? Okay, well, what we're talking about here is a data set about unrelated donors. So there's a whole other genre of related donors. I don't want to, I mean, that, so these are patients who didn't have a match within their family, right? So they needed to go to these big registries to find an unrelated donor. So unrelated donors are matched on these things called human leukocyte antigens, HLA. So there's 8 of 8 matches. And for the data we're talking about, it's recipients from 2016 to 2019. And like I said, the goal is picking optimal donors for better recipient outcomes. So the outcome here is time to event, what we call event-free survival. And event-free survival is really interesting because it has both right and left censoring. I've never seen this in any other data set I've ever worked with. So we needed a method that could handle that. So the events include death, relapse, graft failure, rejection, moderate, severe, chronic, GVHD, whichever comes first. So event-free survival is kind of a composite of all these different types, whichever of those comes first. We have 45 covariates that might have an impact, and 5 of them are donor-related characteristics, which are the ones we want to optimize, right? We have age, sex / childbearing, HLA. So 2 other types of HLA besides the 8, DPB1, DQB1, and CMV match. So CMV match is whether you've had cytomegalovirus in your past or not. So we wanted to learn the likely complex functional relationships between these covariates and the outcome with BART. The cohort has 10,000 patients for training and 1,800 for validation. So this was too large for our discrete time BART. Why? Because when you have to expand it on this grid of times and you've already got 10,000, now you're talking about a data set with 50 to 100,000. And that's a little bit too big for BART at this time. Actually, that's something we didn't really talk about. So there is a bit of a challenge with large data sets. So if you have large data sets, just email me and ask me the question because I don't have time to get into it, at least not right now. Maybe I can come back to that later. But big data sets and BART is a bit of a challenge. But for 10,000, that doesn't seem that big. So we created this new approach we called NFT BART. Well, why did we do this? Okay, so let's look at all of the other published BART survival methods. So those are across the top here in the columns, and the rows are different properties, right? So the first row, let's look at this one. Well, let's go across first. So there's these methods called hierarchical BART methods. Discrete time, that's the one I just talked about. AFT, accelerated failure time. I'll talk more about that later, but there's a thing called modulated BART by Tony Lanero, who's going to join us at 3:30 on Zoom, and the new approach, NFT. So restrictive assumptions. Well, it turns out hierarchical have very restrictive assumptions. Similarly, AFT itself is a restrictive assumption. Non-parametric. Hierarchical are, technically, they're not entirely non-parametric. They're probably maybe semi-parametric, I don't know, whatever. The rest of these are non-parametric methods, right? Left censoring. I don't see any way that you can do left censoring for these 3 methods. Only these 2 naturally lend themselves to left censoring. Computational complexity. These methods are good. Discrete time BART, I've already said, bad, right? Modulated BART, really bad, really slow. I mean, it would work if you could scale it up, but there's just no way. This is good. But notice that NFT is good on all of these, right? So it had all the nice properties we needed. All right, so this is BART, but I just adopted what I call NFT notation. By NFT notation, I mean, now BART, I'm saying BART is, I'm calling this mu of x instead of f of x, right? Where mu of x looks like this, right? So I'm just changing the notation, and you'll see why in a moment. But this is just saying, okay, this is BART and just another notation. Heteroscedastic BART. So this is, I talked about this a little bit yesterday, but we never really got time. We didn't have time to go into the details. So now now I'm going to go into more detail here. So a heteroscedastic BART here in NFT notation is the same. Looks the same, but look at the errors. Now the errors have a function of their own, right? So the mu is just a BART, but notice now we have K is 5 instead of 2. And now we have this new prior, the H BART prior, the heteroscedastic BART prior, and it has all of these same parameters. Well, these first 3 are the same. And now, and it has the number of trees. But notice the number of trees is lesser for heteroscedastic BART, and it has 2 new parameters, right? So now this function, now notice this is a function of trees, but now we're multiplying them together instead of adding them, right? So this is what we call the heteroscedastic BART model, but it's in NFT notation. All right, so now I'm going to talk about accelerated failure time. So what is accelerated failure time? Well, first of all, I'm just going to show you the notation we're going to talk about. So we have a time to event and whether and an indicator if it's an event or not, right? So if it's 0, then it's not an event. It's right censoring. If it's a 1, it's a failure time. It's an event. If it's a 2, then it's left censoring. And what we want to know is how is the failure time explained by some covariates, right? So what is the accelerated failure time approach? Well, they take a logarithm and they use a linear model. Okay, that's a con, right? That's a parametric assumption. This is why I said that it's non-parametric, but it has a restrictive assumption, right? So even though it's not parametric, this restrictive assumption is restrictive. So it's got a negative connotation, right? So y looks like this, plus some error term. Okay. Now the error term does have some. Well, it could be a non-parametric distribution. However, typically it's parametric. It's a con. But as we'll see later on, we can adapt that to a non-parametric. But right now, the plain AFT model, without BART, without anything, is a restrictive parametric model. So I just wanted to explain why they call it accelerated failure time, because I think this. This leads to some confusion, maybe. We'll see. So what you do is you consider a baseline survival function where the covariates are centered. So in other words, they call it S0 of t where x is 0, right? For those. And you can define any other patient. If you go through this math here, you can define any other patient as a function of the centered patients by multiplying this time by this, right? So you're accelerating or decelerating depending on what your x's are. So that's why they call it accelerated failure time. However, this is a precarious restrictive assumption. Like I said, notice that the covariates only affect the survival function through this log linear location shift. That's all they do, and not only that, it's parametric, right? So Henderson and Lewis, they adapted AFT BART to they made the epsilons non-parametric, right? So that's pro. That's a good thing. So I'm using NFT notation here. So they have a BART here, and then to make this error distribution non-parametric, they introduced these random mui's, right? So now it's no longer centered at 0. However, to ensure identifiability, the average of them is constrained to be 0. Okay. And how do they do this? Well, they use Dirichlet process mixture, like so. But at the end of the day, if we get down to the survival function, which looks like this, notice that even after all of that extra work, it can still only explain a log linear location shift. So that's so the AFT. So it's non-parametric, but they still have a restrictive AFT assumption. All right, so this was Rob's idea. So he said, okay, let's do this. Let's use a heteroscedastic BART and to get out of this AFT restrictive assumption. AFT is homoscedastic. So by introducing this heteroscedastic BART, we're exploring. We're getting out of that restrictive assumption. Also, Prakash had done some work on using not just a random mu, but also a random sigma. Okay, so we have a little bit more flexibility there, but now we have two constraints, right? So not only do the mu's have to sum to the average mu's have to be 0, the average sigmas have to be 1. Right, for identifiability. Okay, great. Well, if you have all of that, how do we do this, right? Well, we need one data augmentation step. So if delta is 1, then we observe the event time, and y1 is log t. Otherwise, we'll have to draw it. If it's right censoring, we draw from the right side of the distribution. If it's left censoring, we draw from the left side. Simple. So now, and we have a DPM, but at the end of the day, look what we've got here. We've got a survival function, and now it not only explains a location shift, it also allows rescaling. Now we're out of that acceleration deceleration curve. Now we can we're outside of that restrictive assumption, right? So that's why we call it NFT, non-parametric failure. I just have a quick slide about Dirichlet process mixtures. I think I'm going to skip this in case unless there's any questions. We could come back to that if there's any questions about this. And this is also about DPM, so I'm going to skip that. Well, wait a minute. Excuse me.
Do you need a parametric model for modeling the sigma square?
Can you say that again? Parametric model for what?
For the sigma, you mentioned it depends on the xi.
No, it's a BART. Yeah, so it's a BART model. Let's see. I said I'm going to skip this, but I don't know. Maybe I shouldn't skip this. I'm going to try to talk about this. Let's see how this goes. So in a Dirichlet model, like so, you have these random thetas, right? So you have yi given some random theta from some distribution, okay? And these cluster together. So these theta i's are discrete, right? So there's these discrete values. So so what you end up with k clusters of these, and I call these ephemeral random clusters. Why am I saying that? So I'm saying that because these clusters are allowing this distribution to be non-parametric. They're not trying to detect, what I would call fixed clusters in the data. If you want to talk about fixed clusters of the data, there's a nice article by Geng and Jassa where he effectively puts a prior on K here, and he makes that transition from these ephemeral random clusters to real clusters of the data. But that's not what I'm talking about here. I'm talking about these ephemeral random clusters. All they represent is the non-parametric nature of that's learned from the data. Okay, but not clusters of the data, the distribution of the data. Okay, so why is this different? Well, why is this different just from plain mixtures like Rob showed yesterday, right? He just had regular mixtures. Why is it different? Well, so this data comes from some random distribution called G. Well, that's different. So in just simple clusters, these data just come from some prior F naught, not any random distribution, some specific distribution, right? That's not learned from the data. So if you guess right, great. If you guess wrong, you guess wrong, right? And this is all notation. So the notation goes like this. This random distribution is given alpha. So we say that's a Dirichlet process of alpha and F naught. And what this means is this random distribution G is centered on F naught, right? So I'll explain a little bit more about centering in a moment, but these alpha have some gamma prior typically. I mean, you could put a different prior on it, but typically it's a gamma prior. And this is called the concentration parameter. And this alpha is proportional to K. So in other words, this distribution, this prior affects the number of clusters you're going to get. That's what K is, right? K is the number of clusters. Interestingly, so like if you integrate out G, like you can over the posterior, right? We integrate out G, so then something like this is what it looks like. So the first patient, you draw that just from the prior. And then the second patient, you draw the second one given the first, and you have a certain probability of drawing again the same cluster, right? The same cluster that was just recreated, or you have that probability of drawing from the other cluster. Okay, so that's what DPM, that's DPM in one slide. It's not easy to do, and hopefully you understood that. If not, well, I should take questions on this, because I think Dirichlet process mixtures are so powerful that people need to understand them. Any questions? Okay, I'm glad you understood that. Okay, now we move on to constrained DPM. Now notice we have these constraints. Well, how do we draw these mu's in a constrained way? Well, Yang and Dunstan showed that you can draw them unconstrained and then enforce the constraint. So you draw these unconstrained, and then you find the center of these, and you subtract that off so that you get they satisfy the constraint. And you can do the same thing for sigma squared. Now that's how do I say this? That's a very effective approximation, but it's not the same thing as drawing from a prior that has this constraint, but it's close enough for most people. It's close enough in most cases. So that's convenient, because creating a prior that does this would not be trivial. I think it would be tricky. Or this, right? And especially both of these at the same time, right? Might not be easy. I mean, it's not easy. All right, so Prakash has a paper that explains how to do both mu and sigma. So all I want to say here is, so one of the nice things about BART is it has these default prior parameters, right? So this is what Dr. Laud's work does called Leo, he found a way to set up this this prior. Let's see. How do you set up this prior with some nice defaults, right? And that's what he did. It turns out that, let's see here. I think you should just read the paper, but basically, they create a hierarchy of priors. So actually, you have several priors, and I don't know this slide really does a great job of explaining it, but you can look at their paper or look at the paper we just published in Biometrics, and it shows how to set up the hierarchy and has some nice defaults for those prior parameters. That is really hard to do in general, is come up with DPM. Coming up with those prior parameters is not as simple as it sounds. So this is really a really important work. And that's what we did. We have a package and we have nice defaults, and it generally seems to work. Okay, so I want to talk a little bit about prediction intervals, because I'm going to show some of those in a moment. So this is just our model, right? And what is this distribution of error? So it's a mixture, right? It's a mixture of these normals, right? Well, I want to create a prediction interval, and a prediction interval, I want to create it like this. So I have mu of x plus some constant times theta, sigma of x. That's the lower limit, and the upper limit's like this, right? But what are these constants? Well, those just come from this distribution. So you can very easily calculate this distribution and get those constants to make prediction intervals. So here I have an example. So in this case, I'm calling this the T16 scenario because the error is T with 16 degrees of freedom. I've got 500 patients with 50% censoring. The true f of x looks like this. The true s of x looks like that. And this is what we have here, right? I only have one x here so that I could graph this. It's uniform. Now, let me explain the graph here. So the dots, the black dots, are the patients where we know their event time, right? So these patients have delta is 1. But since I simulated the data, I also know the red dots, which is the event time of the people that are censored, okay? So I trained on the whole data set, but my R squared with the uncensored is 85%. And my R squared with the censored is actually about the same, 85%. I think that's pretty cool. Okay, but getting back to the prediction interval part, so the truth here is in blue, right? And the black line here is our estimate of the truth, or of the center of the mean, right? And the dashed blue lines are the true prediction interval, and the black lines are our estimate of the prediction interval. So we did a pretty good job here. Any questions about that? So Bart learned this complex relationship rather easily. Okay, and then here's, we're going to estimate. So this is that error distribution I was talking about. The blue line here is the truth. The black line is our estimate, and the 95% credible intervals are surrounding it. So we did a pretty good job here of estimating the distribution. The two blue lines here are the actual critical values, and the black lines are our estimates. So right here, we nailed it. We're right on it. And over here, we're pretty close. Okay, so that was with T with 16 degrees of freedom, not really considered a heavy tail distribution, maybe a medium sized tail. Oh, sorry. I have a couple more slides. Anyways, okay. So here, so this was the prediction interval, right? Here's our estimate of just the mean function, and notice our credible intervals for the mean function itself are less than the prediction interval, right? Which they should be, right? The prediction interval is always going to be wider. And here, here's the true S function, and here's our estimate of it. Notice we seem to be overestimating it, but we're getting the shape pretty close, right? It's a rising function, and we're getting that, and it's generally within the credible interval. Okay, so now, like I said, that was like a medium heavy tail. Now I'm moving to a heavy tail distribution. So now the errors are T with 4 degrees of freedom. So the R squared on the training, well, not the training, the R squared on the uncensored is 80.7%. The R squared on the censored is about the same, 78%. So pretty close, right? And the black line is right, pretty close to the blue line, and the dashed black line is pretty close to the. In fact, it's even closer on this one than it was on the other one. It seems to me, right? So we did a pretty effective job there. Okay, here we're estimating the distribution. So you can see the let's see here. The blue line is the truth, and the black line is the estimate. It looks like we didn't do so great in the tails. We did very well up to about here, and that's, you know, it threw off our prediction interval a little bit, our cutoffs. But they're close. I mean, they're not identical, that's for sure. But all in all, fairly good performance, I think. So here's our estimate of the blue line. We were very, very close to it, and it's all within the credible interval. And again, we seem to be overestimating the true variance a little bit, but it's mostly within the credible interval. All right, so let's look at another scenario. So here we have 500 patients with 50% censoring. And we just have one X variable that's Bernoulli. So we sampled the data from a Weibull. The Weibull is neither AFT nor, or I should say, this setting is neither AFT nor NFC. And if you look at the analysis here, you can see that. Let's see here. So I analyzed this data set with an AFT model. Also, I did it with the discrete time BART. Okay, so the truth here is this thick dashed line. You can see that the discrete time model is pretty close to that. Same thing over here, right? So the black line is with X is 0. The red line's with X of 1. But if you analyze this with an AFT AFT model, an AFT BART, you see it misses the truth here. I mean, it does seem to do okay with X is 0, but for X is 1, it totally misses, right? And if you analyze this data set with NFC, you see that we don't have that problem, right? So here's the truth, and we're very close to it. Similarly over here. All right. Any questions about that before I move on? I ran Thompson sampling variable selection here. And you can see a lot of characteristics are coming in here, but most of these are recipient characteristics. We're really looking for our donor characteristics. So let's see here. Yeah, I can't see any, but that's just an example. So this is an example of a TSVS plot. So you can see these variables here are very likely important variables, and the variables down lower may or may not be, right? So here I'm going to show you some examples of what some of this stuff looks like. So there's three major diseases in the data set. So I think about 60% of the data, if you look at ALL, AML, and MDS, those are three of the diseases that are like 60% of the data sets. Well, MDS is disease 5. MDS has a status variable that goes from a risk status, very low, So very low risk, intermediate risk, high risk, very high risk, right? So we modeled this data as an ordinal variable. So it went 1, 2, 3, 4, 5, okay? And this is I'm plotting the marginal effect here. So you can see if you have very low risk, you have the best survival. Low risk is a little bit worse. Intermediate is much worse. High is bad, and very high, they kind of cluster together. So I think this is showing that the model is really picking up what's going on, because that's the type of thing that you would expect to see from a variable like this. Okay, so here's another one: recipient age. In this data set, we had children all the way up to elderly adults. So no big surprise here. Generally, the younger you are, the better your chances of surviving are. So this window here is about how much follow-up time we had. Most people had about 3 years of follow-up in the data that we have. So that's why I'm graphing it on this scale. So you can see the 8-year-olds had the best chance of survival. 33-year-olds, not so good. 57-year-olds getting worse. So that all seems to make sense. Donor age. So now we're getting at, so that I was showing you the recipient characteristics, but we really want to know the donor characteristics. Well, it's a little hard to see here, but 18, 21, 25, and 30, all those lines are right on top of each other, but 40 starts to separate. So what this is saying is, if you have a choice of a donor that's in their 30s or younger, take it. It doesn't seem like a big difference, but like a few percentage difference, you would take that, right? I mean, you're not going to, you're going to go for the younger donor. And if they get a little bit older than 40, it gets even worse. So this is what it looks like on average. But if you boil it down to an individual level, right? So individual level, if I just look at the 3-year survival and I take differences. So the way this curves work here is, so it's 18 versus 24, right? So you can see 18 versus 24, there's really not much difference. That's just about a 0, right? So the survival differential is about 0. 30, still pretty close to 0, but it's creeping up. And then you get to 36, aha. So 95% of the people in the study would benefit from an 18-year-old versus a 36-year-old. And why do I say 95%? Because we have this zone here, plus or minus 1%. We call that the zone of indifference. So that's in optimizing treatments, they usually have some cutoff, some arbitrary number. In this case, we use 1%. So it's got to be at least 1% to consider changing your donor. And similarly for 42, 98% would benefit from an 18-year-old donor. Okay, here's another characteristic, donor sex. And what we call childbirth parity. Okay, so let me explain the lines. So this line here is the recipient is female versus a donor that's male. Recipient female versus a donor that's null parus. That means a young woman who has not had children. And then the next one is recipient female versus a donor of one or more. So this woman has had one or more children, et cetera, right? So now it's recipient male versus those three. So, so you can see here that for recipient male, donor male is the best. That's the top line. That's the gray line. The next line down is recipient female, donor male. So that's kind of interesting. So if you're a female, you're actually better off to have a male donor with respect to EFS, because the rest of them are down here. And actually, if you look at this, if you blow this up, you can see that donor null versus non-null, no children versus one or more children. You see those lines are right on top of each other. So really, the parity itself doesn't matter, just the donor sex. Yeah. So here I've got the same thing. I've got waterfall plots. So like I said, these are the marginal effects. If you look at the individual effects, so these are sorted in order of I forget which they're sorted in order. Oh, here it is. In order of DF0, right? There's not really much difference between DF0 and DF1, so they pretty much are the same. But anyways, so if you have a male donor, sorry, how does this go here? So, oh yeah. So if you switch to a male donor, this is your benefit, right? You can see that there's some people have no benefit at all, right? About 7%, but 93% do. Yeah, about 93% benefit from switching to a male donor. That's if you're a male. And if you're a female, it's not quite as cut and dried. You know what? I'm not sure if this slide is right. I'd have to check this. But let's just read the slide as it is. If this were true, you would see these people don't benefit, these people do, and everybody in the middle doesn't matter, right? And that's the last slide. So now I was going to show you the package. So this is a package we didn't install yesterday. So we're going to have to do that. All right. Oops, sorry. So this one's on GitHub. So that's my username. This is the repo. And then you can provide a directory. So let's fire that off. Not, oh, so you have to load that function, obviously. So let's so this will give you the latest and greatest NFT BART. NFT BART is also on CRAN, but I've made a few changes, not a lot, but a few. So you can always get the latest and greatest. Okay. All right, great. So now if we want to find that demo directory, we'll use our trick, right? And that'll show you where that directory is on your system. I actually have the, I actually have it copied to my desk here though. So I'm just going to open it here. All right, so what have we got here? So we've got several examples. Let's do the lung cancer example. So I'm just going to fire this off. Okay, it's running. All right, so let's look at the code here. Now notice I divided the time by 7, so it's on the same scale, but I didn't use ceiling. So now the time is continuous, right? So we don't have to make those discrete grid, right? We can just use the data as it is. Also notice I didn't do anything with respect to missing values, right? So NFT BART also uses cold decking to impute the missing values. So here I'm calling it, let's see, what did I do? All right, so notice here up here, I'm using, so in BART 3 and NFT BART, you tell it how many cores you want to use with the options MC.cores, okay? And if we look at the output, let's see. The diagnostics tells us how many cores we're using somewhere. Yeah, there it is. Thread count, so 8. Now, so this uses fairly advanced tree rotation. Remember, Rob was talking about births and deaths. This is way more complicated. We've got these more advanced tree maneuvers. There's one called change of variables. There's one called rotate. So this is supposed to optimize the search by doing more sophisticated tree proposals. You're searching the space in a more efficient way. In order to do that, there's this adaptation phase that is before burn-in that sets these parameters to make that search work well. And it's a joint search. Remember, we've got heteroscedastic BART, right? We've got mu and a sigma. So yeah, so that takes a little bit of time, but notice it's going pretty quickly. In fact, it's done. Also in this package, I have this function called C-index. So if you're familiar with the C-index, so what the C-index does is it's usually used for Cox models where you look at that proportionality and you use that as like a risk index, right? And you take that risk index and you use it like kind of like an ROC curve, if you know what I mean. So you have the probability of being concordant. And you can see that you can see what this model is 0.667 concordant. That's pretty high for survival data. Even though this C is the same C more or less as an ROC, you know, obviously you lose something when you censor stuff, right? You don't have as much information. It's not like dichotomous outcomes, right? There's more information in dichotomous outcomes than there is in time to event in some sense, because you only can see the ones that fail. So 0.67 sounds low, but actually for survival analysis, that's probably about par for the course. Okay, so that's done. So let's see. So that's the curve we get. Looks nice. So these are the females. And notice now we have smooth curves, right? Because now we know, you know, we've generated, we don't have that choppy, right? So this is what, like Rob was saying, some people like it smooth. They don't like that jittery stuff. So this model does produce smooth distributions, or smooth curves, right? All right, so that's that. I also want to show you doing a relative risk. Let's see, where is it? Oh, okay, so let's do the relative risk now. Let's see, how do we do that? All right, so we're going to use the predict function. So we're going to set up this X test. And let's see what's happening. All right, now it's predicting right here. I don't know how long this is going to take. So now I can take questions while it's running. Any questions? Well, we're a little bit ahead of schedule. We got 15 minutes to kill. So what do you guys want to do now? Do you have any questions about anything else I've talked about? Well, I should ask, did you guys install this package? Why don't you try installing the package and see how it goes? I'm curious to see if you have any issues. I can tell you, you know, it's really important. This line here, when it's checking for, well, if you're on Windows, you won't get this line because it doesn't know how to do that. But if you're on Mac or Linux, how to do OpenMP? Now, the good news is if you're on Windows, it shouldn't have to think. It's already hardwired to do this, but you just won't get a nice diagnostic like this checking, right? Because it doesn't know how to check. It's just going to try it. You know, it's just going to do its best. Does that make sense? How many are Windows users, by the way? Raise your hand if you're a Windows user. Raise your hand if you're a Windows user.
I'm using Windows now.
Okay, you? No? You're both. All right, so I'm curious. For the Windows people, what happened? Did it work?
My computer is out of battery, but I do have a question. Yesterday,
But you can plug in. There's a power right under your seat.
I didn't have my charger.
Oh, you don't have your charger?
But
We got power to the seats. You got to bring your charger.
I don't want to go out and come back to interrupt. But
Okay.
I have a question.
Go ahead, ask.
Yesterday, I think I mentioned that to you for the OpenMP, right?
Yeah, but you're on Windows. I just said there's no way. You just have to try it. That you won't get a diagnostic like this, right?
Yes.
So the only way to find out is to try it. Let me see here. Oh, here, I have an idea. Oh, it's done. So here's one way to check if OpenMP is installed. So let me see. I forget the name of the function, so let me just check here. Oops, wrong thing. All right, so we created this function that'll help you detect. Like I said, you won't get that nice check when you install it, but we created a function that'll help you check. So here it is. In the BARD3 package, we have this function. This will tell you if you're running OpenMP or not on Windows, Linux, whatever. So see that? So it said, I ran this function, mc.cores at OpenMP. If it returned a 0, you know OpenMP does not exist on your platform. If it is non-zero, then you know it does.
If it doesn't exist for OpenMP in my laptop, I mean, should I install the OpenMP? How should I fix this?
Good question. Okay, so let me bring that up. Oh, let's look at the plot first. So the plot's done. Here you go. So this is what the relative risk looks like, males versus females. And it's pretty similar to what we had before, right? It started a little bit high and it came down. Now here there's something where it went really high, but that's a very short interval, right? Generally, this is around 2 or a little above 2 to a little below 2. And overall, if we assume proportionality, it looks like that. So pretty similar results to we got from discrete time BART. Okay, any questions about this before I start talking about Windows and OpenMP? I mean, we could also talk about Mac too, if you're having any trouble. But first, I'll talk about Windows for 8 minutes. I have only 8 minutes before we have a break, and then we bring on Tony. Does that sound good? But any questions about this first, about NFT? Okay. All right, so I'm not sure exactly which page the Windows stuff is on, so I have to look at this. This is a long document, so let's take a peek. All right, so see here, it's documenting that function that I just told you about. Returns greater than 0 if OpenMP is running, 0 if not. That's regardless of platform, right? But how you get OpenMP does depend on platform. So let's see here. All right, so so this is how it works on Windows. It's not smart enough to detect it, but according to the tools provided, the Ming GW tool, right? These two switches need to be in your makeVars file, right? Source/makeVars. So if those are in there, that should get OpenMP working. Let me see what else. But you have to have the latest tools installed, right? So like I'm not sure exactly what the time frame is, but I looked at this like right around the pandemic, and there was no OpenMP support. And sometime between, I'd say 2000, maybe 2020 till now, they come up with these new tools, RTools 4.3. So if you install those rely on GCC version 12. That has OpenMP in it. Okay. So Mac's sort of similar things have shifted a little bit over the last couple of years. So for about the last year or so, these instructions are valid. Okay. So what Mac requires is just Xcode. So you go in the App Store and you get Xcode, right? So they don't provide a tool set on CRAN. But what they do provide is this library, which is missing. This library does not exist. So you have to install this library. Well, first you have to install Xcode, but then you have to install this library from Mac, from CRAN. See this? Okay. Any questions about that? So I can show you right now. Let's see, wait, I have another page here. I don't know if this tells you anything else that I didn't say. I don't think there's any more to it than that. Yeah. So this is about Mac. Oh, let's see. Yeah, so this is how, so on Mac, this is how you install that library on page 11. Oh, okay, so I was gonna look. So if you're running, let's take a peek. So this is the file you need to check. So in BART3, in the source directory, there's a make fares, right? So this is the one for Windows. So you should see these two lines. That's all you should need on Windows if you have the right tool chain. And for Mac, I already showed it. It actually detects whether you have that library installed as it installs it. Windows can't do that. It doesn't know how to do that. But the library is already hardwired to tell it. So that's BART3. Let's check. Now that's BART3. You will not, I don't think that exists in BART. So let's see. Let's look at the BART package now. Oh, I don't know. Can I get it? Well, first let's look at it. Let's look at NFT BART since I already have that one downloaded. Oh, I have BART downloaded too, I think. So NFT BART, same thing. We're going to look at makevars, right? It's the same, right? Has these same two lines in it. That's all you should need in Windows. Now, is that true of the BART package? Probably not. The BART package on CRAN does not have those. Okay, so that's a good example. So let's do that. So let's see. Do I not have that? Maybe I have to look on GitHub. Let's see. This is the same problem I had yesterday. Let me see. I don't understand what the problem is. Here, let's do this. Wow, there's a lot of packages with BART in the name. Let me see. Oh, I'm logged into the server. Okay, so I can show you on the server. All right, so I'm also logged into Linux server, so I can show you. All right, so in the latest and greatest on the server. Okay, I think I know. Okay. All right, so the BART package on CRAN, I don't think is smart enough. However, if you pull down the BART package on GitHub, even though it's the same version, it has that make bears fixed, right? So let's try that. Of course, I'm doing it on I'm doing it on Mac OS, but this would be the same command if you were doing it on Windows. So now the repo, I think, is called, let's see what happens. It's not called that. What is it called? Oh, I know what it is. It's on Bitbucket. Sorry, I'm on the wrong repo. So Rob and I also have a Bitbucket. Let me see. Where is it? Is that it? What is this stupid thing? How do I get rid of that? Oh, here we go. Yeah, see, it's the latest and greatest. I don't know if there's an install GitHub function though. Let me see. Let's see. Yes, there is. Aha. Okay. So install BIP. So what do I do here? Let's see. See, it says untitled project. I don't. Let's see. How do I do this? Here, let's look at the help. Oh, sorry, we're out of time. Well, I can tell you if you can get the BART source code, which you can get it from CRAN. You just have to change those 2 lines on Windows, or just pull BART 3. Okay, with BART 3 it works. All right, so we're going to take a break now and we're going to come back online at 3:30, and Tony's going to be presenting. Okay, so it's my honor to introduce Antonio Linero. He's an assistant professor at University of Texas. He did his dissertation at the University of Florida. He's of Dart fame and a good speaker and an excellent article creator, I should say. He has almost 800 citations already over the last 5 years. So Antonio, you want to take it away?
Sure. Thanks for the introduction. And as I understand, Rodney and Rob have covered the basics of BART. So I just want to talk about some other ways of applying BART models to that go beyond the problems where you can leverage the conjugacy of a normal distribution. So this would be settings like the standard semi-parametric regression model or the probit regression model, but even things like you can do logistic regression using kind of tricks related to normality. But there are some problems where you can't. And yeah, I figure I'll just talk about sort of filling that gap and talking about models where what do you do if you want to fit a model that does not conform to kind of the conditional conjugacy of a Gaussian distribution. The broad aim is to fit models, embed a BART model inside of whatever model you're interested in, and not be constrained by conditional conjugacy. Roughly like to introduce enough tools that you can fit any model basically that you could cover with the GLM function in R. So if you wanted to fit a generalized linear model in R, you'd have access to the normal logistic, but also things like Poisson log linear model, negative binomial models, gamma regression models. So all of those things that you might want to use a BART with, and basically have BART function as a drop-in replacement for whatever linear predictor. So if you have a model that would have a linear predictor, how do I go about just swapping that out with a BART model? And then most of the tools, that Rodney has presented for things like model summarization, all that. I won't talk about all that stuff, but it basically should all port over fairly easily to these settings. Right. So yeah, we'll talk about other problems of interest as time permits. I guess I have an hour, but I don't necessarily have to get to all of these other things, but things like estimating conditional distributions, handling sort of other non-parametric models like Cox proportional hazards model with a BART in it, and some other modifications to BART that that folks have developed over the years, including applications to address the fact that decision trees are sort of inherently non-smooth. And I'm going to focus on covering a large number of things with maybe superficial depth. But the hope is that if you identify that you have a problem that could be addressed by one of these techniques, that you'll have something to follow up on later. Not going to go into a ton of detail on any particular thing, and just try to give you enough to know what to look for in the literature. I'll be talking about a class that I call a generalized BART model. So as input, you have a parametric family. So I have P sub nu. Nu is taken to be a nuisance parameter, finite dimensional parameter. So for a non-parametric regression, this might be the error variance, but it could be all sorts of other things that parameterize the model, but you're not trying to model it with a BART. So I have some parametric family, I have the outcome, and I have basically a mean parameter that I would like to model in a flexible way as a function of the covariate. So this mu will be real valued. The nuisance parameter will take values in some set, so nu for nuisance. And then the generalized BART model just takes this and replaces the mu with an ensemble of decision trees. It's a really kind of straightforward idea. Now, to get these models to work, and I'll give some concrete examples in a moment, but in order to fit these things, so it's one thing to write down a model like this. It's perhaps another thing to fit it. And if you look at the details of the Bayesian backfitting algorithm that I assume was presented at some point during the day, it turns out that what you need to derive a Bayesian backfitting algorithm, so if you have a model, P nu, and you want to derive some Bayesian backfitting algorithm, then it suffices for, if you have a model that looks like this, y is distributed P nu with parameter mu plus lambda I. If you can write down this model for arbitrary choices of the lambda i's, if you can write down a conjugate prior for mu or a conditionally conjugate prior for mu, then it's possible to derive a Bayesian backfitting algorithm. So in the context of a normal regression model, what this would basically be is mu would correspond to, so this would be a normal distribution, nu would be the error variance, and lambda I would basically be the kind of this backfit quantity of the sum of the predictions over all of the trees except for the one I'm trying to update. So if I'm updating tree T, lambda I would be the sum of the decision trees except for tree T. And then this would sort of be the leaf node parameter that I'm trying to update. So if you can write down a conjugate prior for this mu within that context, then you can do the Bayesian backfitting algorithm. Once you make that realization, you might then try to look for other models. So this is true for the normal distribution. If I put a normal prior on mu, I can get a conjugate prior. Well, it's conjugate. And basically what that turns into is I subtract lambda I here, and I kind of get these backfit residuals, and I'm able to do an update for mu. But there are other models where this trick actually goes through. And most of them, or all of the ones that I'm aware of where this trick actually goes through, aside from the normal distribution, make use of a log gamma prior for mu. So this isn't my idea. My colleague Jared Murray came up with this idea. Actually, if you saw the heteroscedastic BART model, it's actually a very similar idea. In a lot of ways, it's kind of the same idea. So credit to Jared, and also as Matt Protola and others who came up with this model for the variance. But yeah, this is the basic idea. And hopefully Rodney will share the slides. There are some links to the papers throughout the slides. So if Rodney shares it, and you click on the link and open it, you'll see it has this this nice paper that Jared wrote that you can look through for more details on this model. Although actually Jared uses this kind of slightly more complicated model, but don't kind of worry about it. It's slightly more complicated than a log gamma. Now, if you want to use this kind of log gamma prior, so basically take the leaf node parameters in this ensemble to have log gamma priors, a very important thing in implementing or using BART priors is this use of the regularization prior. So putting an appropriate prior. And now basically what you end up doing there, specify some variance sigma squared mu, or maybe Rodney wrote tau squared in the slides, and then you divide it by the number of trees. So the ability to do that is important for kind of appropriately regularizing a BART prior. And it's easy to do for a normal distribution, but how do you do it for one of these log gamma priors? So a useful fact, if mu has a log gamma prior, by the way, a log gamma prior is just the logarithm of a gamma random variable. So if I have a gamma random variable and I take the log of it, that's what I mean when I say a log gamma prior. When you have a log gamma prior, you can get the expected value and mean, so the mean of the prior distribution and the variance of the prior distribution fairly easily. And they're related to these digamma and trigamma functions that are basically the derivative of the logarithm of the gamma function is the digamma function, and the second derivative is the trigamma function. So you can derive in closed form the mean and the variance. And to do this calibration, what you want is to have the mean of this thing to be 0 and the variance to be this suitably normalized tau squared divided by the number of trees. So these these quantities basically tell you how to do that. So you can derive, if I want to do a log gamma prior with shape parameter A and rate parameter B, and I want to choose the variance to be this sigma squared mu over H, then you can derive explicitly the formulas for A and B. So A is just apply the inverse of the trigamma function to get A. So I want the variance of mu to be sigma squared over H, just apply the inverse function of the trigamma. That gives me a formula for A. And once I have A, I can get B. And it's just E to the digamma of A. So that's at a high level, you can get exactly a mean zero and variance, whatever you want it to be by doing this. It's, you know, it's not difficult to actually compute, right? These are special functions, but they've been built into various packages, so it's not difficult to do this. Now, if you don't feel like, you know, downloading these, you know, using these special functions, or maybe for some reason you can't implement the special functions, there is a very good approximation that is just take A to be H over sigma squared mu, and B equals A minus 1/2. This actually turns out to be a very, very, very good approximation to give you a mean zero and variance, whatever you want, random variable. And it's a good approximation, in particular when the number of trees is very large. So the recommendation we often make, say 50 to 200 trees, something like that, that's going to be more than enough for this approximation to be good. Now, the next thing you might say is, well, okay, that's all well and good, but you know, what the heck is this log gamma prior? I kind of like normal random variables. And you know, if I'm doing this log gamma thing, I don't like it because I'm not used to thinking in terms of those. Again, if H is very large, it turns out that actually these log gamma priors are very, very close to a normal distribution. So you kind of are almost doing the same thing that you would normally be doing. And this slide gives you a comparison. When you take the variance parameter to be, or rather the standard deviation to be 1/2 divided by the square root of 50. Square root of 50 because, you know, I'm imagining a situation where I'm using 50 trees. So if I have 50 trees, I'm going to be normalizing this thing by the square root of 50. And you can see by the time you get there, I have in orange the normal distribution, and in blue the log gamma distribution, and they're basically the same thing. I mean, they're not exactly the same, but they're sort of close enough that there's no way that using one or the other is going to make any difference for doing inference. So you can kind of freely use these things without thinking too, you know, you might as well just be using a normal distribution. The difference is that by using the log gamma, you get this conditional conjugacy that lets you push a bit further from the models that you've seen so far. So now some actual examples where you can do this. And I guess maybe the most important one is addressing count data. So, you know, you've seen normal regression, you've seen probit regression, you've seen probably logit regression, and various types of survival models. But a very common type of data is count data. And the count data problem doesn't play nicely with the normal distribution. But it does play nicely with the log gamma distribution. So if you have count data and you want to model the rate, you can specify a log linear model. It's also possible to do negative binomial models, which is kind of the over-dispersed version of the Poisson distribution, right? So the Poisson is limited because the mean is equal to the variance, and the negative binomial kind of gives you an additional scale parameter that you can vary to make those things not equal to each other. But both of these models can be handled by this log gamma trick. And I'll walk through the calculations for the Poisson model just to illustrate the point. So if I have a Poisson model that looks like this, is y given mu is Poisson with mean m to I times e to the mu, and mu has a log gamma prior, then I'm going to show that basically this gives you a closed form marginal likelihood and and get the posterior of mu. So if I write down the likelihood for this times the prior, then this is what pops out. So this is a Poisson likelihood, which is where you get your kind of lambda to the y over y factorial stuff from. and multiply it by the log gamma prior, and you smush things together in the appropriate way. This is the expression that falls out. If you kind of squint at it, it actually still is in that log gamma form, right? So to rewind a bit, right, this is what the log gamma prior looks like, and the important thing is that it's e to the a times mu minus b times e to the mu. And if we interrogate the expression that we have here in the Poisson, we have, oh, I'm actually missing a mu here. I apologize for the mu sitting out here. It's thing times mu minus thing times e to the mu, and therefore it's still in that log gamma form, right? Just need to add a missing mu here. So if you do that, then it's possible to integrate this. Just turns into the integral of a thing that we know how to evaluate, and this is what falls out for the marginal likelihood, and this would be the marginal likelihood that would appear in all these Metropolis-Hastings ratios for updating the trees, and also the full conditional of mu. And you can read off of it, because this is still in log gamma form, that it's another log gamma with parameter shape a plus sum over I yi and rate b plus sum over I of the lambda i's. So the Poisson is really nice. It doesn't even involve any kind of data augmentation. You can just do Bayesian backfitting more or less unmodified. It's actually even easier than the normal case where you have the variance parameter update. So Poisson's very nice. Okay, so thought I would just illustrate this in a familiar setting. So I have case with n equal 250 observations and 250 predictors, and I'm just using this sort of Friedman function that may also have appeared earlier in the day, but it's nice because it has a it should be pi x1 x2. It's nice because it has a nonlinear interaction. It has a couple of nonlinear terms and also some linear terms, and 5 relevant predictors, which means 245 irrelevant predictors. This should be a difficult problem. Right, we have n on the scale of p, and we're trying to do non-parametric regression, but we do have sparsity to kind of help us. Hopefully my code will work. I had to switch to a different setup here. Let me see. If you want to do this yourself, unfortunately, the package isn't available yet. The package in the source code here that actually implements it is called Batman, which I don't remember where that comes from, but it has something to do with Bayesian additive and then some other stuff. But that's not out yet, and I need to find a new name anyways, because there's actually already a Batman package on CRAN. But okay, and if you want to do this, if you have a burning desire to do a Poisson BART, you can contact me, and I can give you the package that will do this. I'm gonna load it up. Load up all the things, and got a stuff here for generating the data. I'll simulate it. All right, so this is all just, nonsense of setting the baseline parameters and generating the data. That's all that's sort of going on here. And then the function you want to apply is this Pois-BART, or the Poisson BART. And you just, right, you feed in your design matrix, you feed in your outcome, right? The outcomes are counts. We've got this kind of counts. Feed in a test set. And then you feed in also the splitting probabilities that you want to use. That turns out that you do something like this. But okay, then you do a number of trees and various hyperparameters, and then kind of run it. Oh, what happened? I didn't load it. What's going on here? Yeah, it should be there. Why isn't it running? All right, this is what happens when you switch to a new setup.
It looks like it's looking for it in Batman, but is it a free function?
This did run on my desktop, so frustrating. But I just installed this package in the process of moving over. That's a bummer. It's a pretty interesting example. I can't imagine why it's not finding it.
It looks like it's not in the namespace of Batman. That's all. Oh no, it is. Huh.
Yeah, I mean, it seems like it's not finding the RCPP. Something's going on with the RCPP. It looks like maybe it didn't export it for some reason. All right, this is not the best time to debug it, but believe me, it would have blown your mind.
Yeah. But could you just talk about the future? I know you're working on a package. What are your plans in the near future?
Near future, I'm not sure. I actually could, if I can log on in a second session, I could. I mean, I'm staring at it on my desktop. Maybe. I don't know if I can. All right, this is going to be really.
You're saying that
you're
going to log
in. But if I turn my computer around, you can actually look at look at the what the results are. So
you can log in from the other computer. I think this should be allowed.
Well, I can't. I don't think I can do two sessions at the same time, unfortunately.
Okay.
Like it'll yell at me. But like if I don't know if you can kind of. I don't know if you can see that. So this is on the. Can you see that? Got like a little figure here.
Yeah, it's kind of small. Oh yeah.
You got like the predicted value of the function on the x-axis and the true value on the y-axis.
Yeah, it's
so we're doing pretty good at picking it up.
It's kind of pixelating, unfortunately. So, but we get the gist.
Okay. All right. Good. And then if I also made a plot of the posterior inclusion probabilities, because remember there's 250 predictors and only the first 5 are relevant. So this builds in this kind of Dart prior that does the variable selection, and you can see it's picking out the 5 relevant ones. That's probably not so easy to see, but there are 5 relevant predictors that it assigns a posterior inclusion probability of 1, and then everything else gets pruned out. So all of the other variables have a posterior inclusion probability of basically 0, and the 5 relevant ones get a posterior inclusion probability of 1. Sorry, what?
I saying that figure, we can actually see that one. Yeah.
Okay. All right. Sorry, that's I guess the best I can do. But yeah, and as far as plans for this stuff, oh, maybe I should have closed all right. I should have closed my window because probably it showed up in a really tiny window.
No, we have actually 2 screens on our other screen. We saw it, but yeah, it was fine.
Okay. All right. So yeah, this code I plan to release it. And if you contact me, I'm happy to share it. It's not quite up to CRAN standards, but what I'm hoping to do in the I don't know, over the course of the next let's say 6 months or so is package up all of the sort of log gamma stuff into a package that also will interface with the other packages. So for me, I envision kind of making a package that replicates all of the all the things that you would want to use a GLM for, plus maybe some of the survival stuff. Not rewriting all of the stuff, but just kind of calling existing packages, except in the cases like this Poisson model where there isn't anything. So if I want to fit, I don't know, like a accelerated failure time model, package should call Rodney's code. And if I want to fit a Poisson log linear model, to call the call this code. So that's what I'm planning on doing. And all right, but I think I can move on. Should I go in? All right, going comfortably. Yeah, so that's Poisson log linear model. It also turns out to work with the Cox proportional hazards model, which is interesting. So if you want to fit a Cox proportional hazards model, so you already have tools that give you accelerated failure time model, even one with a non-parametric error. You can do that if you're doing survival, but you can also do Cox proportional hazards model with the non-parametric model for the rate function, or the cumulative hazard. Deb Sinha showed basically that if you write a model that looks like this down and you use this particular non-informative prior for the baseline cumulative hazard, that this model actually reduces down to the Cox partial likelihood. If you want to use Cox partial likelihood, again, you can do it pretty easily with this log gamma trick. And there's details in a paper. And yeah. So I have another illustration, this time not in code, but actually in the slides. So it's PBC data, which is I believe kidney failure data. A fairly standard type of problem you might want to use the Cox proportional hazards model on. And trying to predict, in this case, there are multiple different endpoints. So you either disease, progression, or death. So there's more than two statuses, but for the sake of this analysis, either of the progressions we'll take that to be the event, and then some individuals did not experience an event. Yeah. Different treatments and different ages and so forth. But I fit to this data both a accelerated failure time model and a Cox proportional hazards model, just to kind of compare them. And the accelerated failure time model and the Cox proportional hazards model produce estimates. So the BART estimates, the things that actually get out, even though they're not comparable one-to-one, right? A hazard is not the same thing as an acceleration factor. Nevertheless, they're like pretty highly correlated with one another. So basically these models give the same predictions. In orange here is the estimated survival function for an individual using the Cox proportional hazards model in orange, and orange over here. So no, pretty similar, but there is kind of a difference in terms of so overall, like this particular subject, very bad prognosis. The models agree that they have a bad prognosis. Subject 2, relatively better prognosis. The Cox model is a slightly higher, slightly better prognosis than the AFT model. But you can compare this to some other models. So just to kind of try to sell the usefulness of BART in this case, I did a little cross-validation experiment using the held out deviance, so meaning -2 times the log of the partial likelihood, evaluated on held out data against a bunch of different alternative models. So one using a GAM, so replacing the function f with a generalized additive model. That was one of the models under consideration. There was the BART model under consideration, and then just a linear model. And then it turns out if you know exactly what transformations to make to the predictors, you can do better than the BART model. So there are some variables that really need to be, meaning some of the predictors need to be transformed before they do a good job. But and this is one of the things that I like about BART models, is that you get good performance without having to data dredge and kind of actively look for things. So if you have your data and you run it through, you try a bunch of stuff, it's possible to come up with a model that will do better in terms of prediction than the BART model. But then you have all these sort of you kind of have a lot of researcher degrees of freedom, and the BART models kind of work really well off the shelf and get you almost all the way there without you having to worry about all these kind of multiple testing sorts of issues. So it is possible to do better than the BART model in this case, but only if you kind of know upfront that you need to do certain transformations. And in this case, it turns out that you want to take the log of bilirubin, which maybe if you're a subject matter expert, maybe you know that, but I didn't. So anyway, but yeah, you get almost all the way to the performance of the best performing model just by using a BART. And interesting that you do quite a bit better than a generalized additive model. Because I don't know, I find that interesting. So there are some diagnostics that you can look at, and for the sake of time, I won't spend much time on this. If you're, especially since many people might not be too familiar with the diagnostics of survival analysis models, I'll just tell you what this more or less says is that bilirubin, you need to take a log. That's kind of what these two plots tell you, that you really need to take a log of bilirubin, or do something like that. Or log bilirubin does a better job. And this plot down here turns out to say that basically the proportional hazards model is not valid. So you have the Cox model, and I fit a Cox BART. It turns out that the proportional hazards model is violated for this data set. And that's something that's actually already kind of known. It's one of the things that's known about this data set. The bottom plots are, I don't think we'll get time to do it, but kind of a more flexible model than this one. So Rodney has these non-parametric survival models. Very similar model, gives you a picture for the survival functions that looks like this. And you can kind of see from here that it's proportional hazards model is not satisfied for this data set. But you can go further than Cox. You can do these kind of non-parametric models too. Now, one more example of this log gamma business. It turns out to work for gamma models as well. And this is another type of model that you can fit with a GLM function. Right? You can set family equal gamma if you want to do a gamma response. There are some fields where that's kind of a thing that is relatively common. So people might model things like rainfall with gamma distributions. There are other kind of niche areas where things turn out to be fairly well modeled by gamma. And you can do this basically with the with these log gamma priors. You can fit a BART model to gamma data. So I looked at this in a paper that had slightly more going on, that uses a thing called a shared forest, which is basically a model where you have multiple different outcomes. So I have, say, outcome 1 and outcome 2, and I want to borrow information across them. One thing you can do to borrow information across tasks is use the same decision trees. So you can use a BART model for each of them, but have the same decision trees. So that can be useful in certain situations. And there's a paper here that outlines how you do that. I use this mainly, I mentioned this mainly just to illustrate the use of this gamma model, because that also is the place where we kind of work out this gamma model for outcomes. And we use this model in the context of modeling income data, which turns out gamma model not actually all that useful for that purposes, but it's something that you can do. So we have this medical expenditure panel survey, where the outcome we were interested in was overall medical expenditure. So medical expenditures are positive. So you might think you model it with a gamma distribution or a log normal distribution or something like that. The hitch is that there's a lot of zeros. So there's some people who have zero medical expenditure. So it's actually a zero inflated sort of thing. I have it says zero inflation, and then you have a continuous or roughly continuous positive part. So we used a 2-part model using the same forests, modeling, like you either have no medical expenditures, you model that part, and then if you do have a medical expenditure, model it with a gamma distribution. So that's what we did. Yep, model whether you're a zero or not with the BART, Bernoulli probit model, and then a model for the gamma part, positive part. A slightly better model is actually to do the same thing, but use a log normal model. So the best model we found for this data is actually this 2-part model where you have a Bernoulli probit model for the probability of a zero, and then one of the heteroscedastic BART models for the log of the medical expenditure. So yeah, actually somewhat complicated. You have 3 BARTs kind of floating around, one to decide whether you're a zero or not, one to decide the mean of the log of the medical expenditure, and then another to decide the variance of the log of the medical expenditure. But this model turns out to work actually really well for suspiciously well. Like I've never seen, well, I'll show you. I have these QQ plots, and this is kind of the model for the for this log normal model. Very, very good agreement with the normal distribution. Gamma turned out not to be so good, and well, you can expand the model slightly using a generalized gamma, and that improves it a little bit, but not that much. So the best model for this data turned out to be the log normal, heteroscedastic log normal model. And you can read out some kind of interesting things from this. It turns out if you go through this whole process and you so again, this medical expenditure data is there's a lot of interest in it, and there's a lot of things that are basically known about it. One is there's known mean variance relationship that folks have, that you can, like, you download a paper and they say like this is how the mean and the variance are related to one another. And it turns out to recover it. Basically, the slope of this relationship between the log mean and the log variance agrees basically with what people say it should be. But you also pick out these other interesting mean variance relationships. Like, it turns out for some reason that the number of dentist trips, even holding the medical expenditure constant, the number of dentist trips has something about the variability of the outcome. So you can do a little bit more than just giving a functional relationship. For the sake of time, I'm not going to do these simulations. I'm not going to talk about this. All right. So that's a lot of log gamma stuff. But now what happens if you, whether the model is not conjugate? even it, right? So the normal stuff doesn't work, and also the log gamma stuff doesn't work. So what can you kind of do in that situation? Which the log normal stuff and or log gamma stuff and the normal stuff cover a surprisingly large range of all the stuff you might want to do, but it's not quite everything. So I have a paper that shows how to deal with this in the most general setting using a reversible jump Markov chain Monte Carlo algorithm, and details here. But the high level idea is you write down the likelihood function for a tree, and an idea is to approximate this integral using the Laplace approximation. So this is something that folks have done with these decision tree models before. Say you have this intractable integral, I'll just approximate it using a Laplace approximation and go through that. The neat thing about this paper is actually it does this, but it also has a correction that makes the updates exact. So it's based on a Laplace approximation, but the Metropolis, the MCMC is still holding the right posterior distribution intact. There's software for this. Again, it's not released. But I've implemented this for a whole bunch of different models. And one thing you might want to say, or one way to sanity check it, is to take a model that we already know how to fit and see how it does relative to that. So for the Bernoulli-Logit model, I think Rodney probably talked about how there's this scale mixture representation and a data augmentation scheme that lets you do the logistic regression. If you didn't, just believe me, there is a way to do logistic regression using the BART package, but it's based on data augmentation. If you do it with reversible jump, well, I did both, and this is what you get on a trace plot of the log likelihood on held out data. So this is using the BART package, and this is using reversible jump. And the only thing I want to communicate here is the reversible jump MCMC algorithm is mixing correctly, and also is competitive in terms of performance with the BART package. It has a slightly higher held out log likelihood on average. I wouldn't read too much into that just because the software is different, meaning like the packages use slightly different priors, so the results aren't comparable one-to-one. But it does suggest that the model, the software is fitting the model correctly, and it's mixing. It's mixing almost as fast as this data augmentation scheme.
Tony, can I ask a question?
Yep.
So what was the comparisons in speed? Because the logistic is typically pretty slow with the BART package.
Yeah, off the top of my head, I don't remember, but I believe that they were on the same order in terms of speed. I can't remember if one was slightly faster or slightly slower. I suppose I think I put it in this paper. Let me see if I can. Actually, I don't know if these changes made it up onto archive. They're basic. I mean, they're comparable. I want to say the reversible jump was slightly faster, but I actually don't know. I will say I believe that the BART package mixes, like, I mean, they look like they mix basically the same, but the BART model does mix slightly faster. Overall, I'd say it's a wash. Yeah, they're pretty similar. Now, the main issue with using this, I mean, so I didn't put any of the drawbacks in the slides. This will generally be slower than like the most optimized BART models. So they make very fast, like dBART's BART machine. Those are very, very fast models. The drawback with this, the Laplace approximation, is you have to compute the Laplace approximation for every time you're trying to update a tree, which it's hard to predict how much of a slowdown it is, because there's sort of this optimization algorithm in the middle of this of the MCMC, and could be fast. Like for some problems, the algorithm for doing the Laplace approximation is like very, very fast. And for some problems, it's slower. The selling point for this is, right, so I wouldn't tell you use this reversible jump for the Bernoulli logit. I would say just do the data augmentation thing, because there's no need to kind of do the reversible jump. But if you have a problem where you can't do data augmentation, then this is an option. So to me, this is a last resort. I wouldn't want to do this in general. Okay. Then I'll talk. Yeah, I'm running low on time. This was ambitious. I have no way I'm getting through 50 slides. But yeah, so you can do some other AFT survival models as well. So I have log T function I want to estimate. You can do this AFT survival time model for normal, but there are other families that you might want to have an error distribution for. One that people like to do is a log gamma, because it nests a bunch of the alternatives. Meaning like a normal is kind of a special case of a log gamma, and the exponential is a special case of a log gamma. Weibel will also be kind of captured by the log gamma. So it covers a lot of possibilities. And if you're interested in the error or the hazard rate or the shape of the hazard function, or trying to decide between all of these different parametric options, the log gamma is one that lets you cover a lot of ground, but is not available by, at least if there is a data augmentation scheme, I don't know what it is. Yeah, basically just take epsilon I to be a log gamma with a alpha alpha shape parameter, and so we've hit a few of these, giving comparisons, and as is often the case for the AFT models, the estimates of this function f like don't change a ton if you change the error distribution. It's fairly stable, although they don't agree perfectly. So if you do the generalized gamma, you basically recover the log logistic predictions. You don't, the Weibel, there's kind of a little bit more disagreement, but they're basically, I mean, they're basically kind of giving you the same thing. But you do get quite different estimates of the hazard function. So property of the log logistic is it has this kind of, I don't know what you would call it. All right, hazard goes up and then goes down over time. The Weibel has this property where the hazard is only going up, and generalized gamma kind of lets you decide based on data, do you want to do kind of a hazard that's shaped like this or a hazard that's shaped like this? Not a ton of, you end up with these really wide bands because it's, well, it's hard to learn about the hazard rate for people that are way out in the tails where you kind of don't observe much.
Yeah.
But
Can I ask a question?
Yep.
So I'm blanking on Valerie Pointer. I don't know if you're familiar with her work. They've looked at models like this where I think it's Pareto and something else. But yeah, it's okay. It's Weibel, but they have like a Pareto prior, I think, on the Weibel parameters, and that gives you a lot of flexibility. So I'm wondering, wonder if the reversible jump could fit something like that.
Yeah, so there are a bunch of other survival models. I talked to this guy. I'm not gonna remember his last name. His first name is Javier, and he's at UCL. He's done a lot with these kind of different ways of bringing in the there's a bunch of survival models that are kind of outside of this area where I've thought of they would be good use cases for the reversible jump, because if you so there are some models where right, there's a way of putting together the AFT model and the Cox proportional hazards model by having kind of two linear predictors. So like one is kind of outside the hazard function and one is inside the hazard function. So you have like an acceleration and a proportional hazards term. And yeah, Javier was interested in these kind of things, but that would be the type of model where you would have to do something like reversible jump because there's no not really any way to go around it. But their aim, yeah, some folks like these parametric survival models. I like non-parametric. I mean, I like the one that you have, right? The sort of discrete time model. That one works. I mean, I'm a non-parametrics person by heart. I always see people using these parametric models, and I'm like, I just wish I could do a non-parametric one. But also you have like these non-parametric.
Well, I think that's what I'm thinking. Somehow, if you do, well, whatever. Actually, I shouldn't sidetrack you. You've only got a couple of minutes left. What do you want to say in the last few minutes?
Yeah, let me see if there's any. Oh, yeah, I have this. Oh, okay, yeah. So I'll end with this. The last stuff was just all of this soft bar nonsense and a bunch of density regression stuff. The last thing I want to make. So this is like something to. I don't know if folks are excited about BART and they want to, and you kind of are wondering what the vision for the implementing this stuff is. Let's kind of show you what the code will look like, because the hope is I also need to find, so I said I needed to find a new name for the Batman. I also need to find a new name for the function here, because Samir has also something called a flex BART. But yeah, so the aim, this is fitting the same model that I fit before, right? So this is the Poisson model, and this is the same exact model, but using reversible jump instead. So I generate all this stuff. But to fit the model, rather than providing the model, like say family Poisson, it's fit by writing your own likelihood function. So I just wrote a little function that evaluates the log likelihood of a Poisson, and then pass that into the packet, right? So pass it into this function, and unfortunately I can't run it because of switching to this other computer. But this code does run, and it runs. It's a little bit slower than the Poisson model, but not by a ton. So you can imagine if you have some model you want to fit, you write your own log likelihood function, and then you just drop it in here and let the BART take care of it. The only downside right now, and this is the thing that I want to iron out over the next few months, is handling updates for the nuisance parameters. So it's easy to do this with the Poisson because the Poisson doesn't have any nuisance parameters. But that's kind of the one thing that is missing. But then once you do that, you write whatever likelihood function you want, and you'll take care of updating the trees and updating the nuisance parameters and all that stuff. But it's just a matter of doing it. Okay, yeah, that's probably a good place to stop for me.
All right, that was a great talk. Any questions for Tony? I'm going to check to see if there's any questions online. Yeah, I don't see any questions online, but I am curious. So you said the GBART package, you say it's not released yet. Is this what you were talking about before, or is this a different animal? Because it's reversible jump.
Yeah. So I need to get the ecosystem straight. Probably I should be merging these two packages together. But yeah, this one is the sort of thing where as I'm writing this down, this is the one that kind of would be basically you specify, let's say you want to fit a BART, you have some syntax for a BART, but you can also tell it what package you want to use. So like you can specify an engine and things like that. And then but that's also where this reversible jump would be living. The other package is like all the log gamma stuff is in its own package. So there's two, but I should put them together.
Yeah, I'm just a sort of a comment, I guess. So we did a lot of work with the log gamma from a different perspective, but it was kind of the same idea, but we never really, I don't know, we never really got the code working. But I think it was the same sort of idea where we were saying there, we had like a hazard BART function that had gamma, gamma leaves, log gamma leaves. Yeah.
Oh, right. Okay. So also the log gamma leaves. I mean, it works for the heteroscedastic BART, because it really is the same idea. Like that's just right. It's a special case of the log gamma stuff. Yeah, I've always found it worked pretty well.
Yeah, no, we didn't think of reversible jump. We had a different way of doing it. Like, as I recall, it was we were using mixtures because you can approximate log gammas with mixtures. Right. But that's probably not the right way to do it. I think you've got a better approach.
Well, so the log, yeah, I know there are these tricks, right, that you can approximate a distribution, maybe like a mixture of. Well, there's like a mixture of normal tricks for the logistic.
Right. And we were going to take a similar trick for log gamma, which actually I think would have worked, but I think I don't know, we gave up on it for some reason.
Okay.
I think this is probably
the log gamma thing pops up in a whole bunch of model. I mean, so I guess I haven't even talked about all of the other places it shows up. It's also useful for hierarchical models. So if you have hierarchical binary data, it's often, so there's kind of like sometimes you end up using these kind of conditional likelihoods. So you don't want to model, if you don't want random effects, then you can do these kind of conditional likelihood models, and it pops up there too.
Can I ask a question about that?
Yeah.
So in your modulated BART paper, I think you made a comment something like, if you're doing those hierarchical tricks with BART, that somehow that doesn't work. It's like it's not identifiable. Can you just comment on that?
Well, I don't remember what I said.
I think you were commenting on Bonato's work. What is it?
Oh, right. Okay. Yeah. Okay. So this is that work in particular. Wait. Okay. So if I'm remembering right, that paper, what they do is they have a parameter, and then they add a normal error to it. Right. So they.
Right. Something like that. Yeah.
Yeah. I mean, like, so I mean. That particular trick that they do, that's also something where it's like you can fit a BART to anything. So what, like if you use that trick that they use in that paper, you can also fit basically any model. But like the catch is kind of in the all right, yeah. So let's say, for example, so what the Bonato paper would do is, and this is what they do in the paper, is like, instead of having it be f of x, have it be f of x plus a little error, like a little normal, like almost like a jitter. in the spatial setting. And if you do that, then you can basically update the f by, sorry, instead of it being e to the f of x, have it be e to the w, and set w equal f of x plus a little error. And so you've kind of like created this hierarchical structure where now you can update the f using the w's and update, you know, this thing also. Like, so you kind of, it's a way of severing the connection between the model that you kind of can't deal with and the BART that lets you get all the normality. The issue with doing that is, like, if it really is a proportional hazards model, then the error variance that you get should be 0. And so it's like, basically you should expect to run into MCMC mixing issues. And it's also, yeah, probably not particularly well identified in terms of like that variance parameter. But so that type of strategy is one that I've been kind of skeptical of. But I mean, it can, there are situations where I think that type of thing could work pretty well. Well, I mean, you know, but they have this paper where it does seem to work pretty well for the survival models that they're looking at.
Yeah, but it seems like that method's kind of fallen out of favor. I don't see it used that much.
Yeah, I mean, because it should be so that trick should be applicable to a whole bunch of different things, and people don't use it. And I suspect it's probably because they run into these kinds of issues.
Right, but your method avoids that, right? So you actually.
Yeah, I mean, the other problem with that method is you don't actually get a proportional hazards model. You get something that's like a mixture of proportional. So it's like, it's also not quite a proportional hazards model, which isn't like, all right, that's not a big sin to not have exactly a proportional hazards model, but it is a difference. But yeah, for the proportional hazards model, yeah, you don't have to deal with kind of anything. It's more or less a straightforward application of, it's like there's like 2 phases. You update the trees and you update the fees here, the baseline hazard. So it yeah, I mean, it just goes like very straightforward.
All right, so I'm just checking the chat here. Any final thoughts? Anything you want to say finally, Tony?
Oh, for me? No, just yeah, thanks for, I'm always happy to shill my stuff. So yeah, thanks for roping me in.
Yeah, I kind of wish we would have had more time for you, but through this Zoom, it's challenging. Like you had to change computers and all that. So I guess it was fine the way it was. But sometime we'll have to get you here in person and for a talk.
Yeah, I mean, so are you at medical?
At the Medical College of Wisconsin in Milwaukee.
Okay, for some reason I thought maybe you, well, I know that's where you are. For some reason I thought this was at Wisconsin. Because is Samir there? He said he was going to be there.
Yeah, he just left like a couple hours ago, right?
He didn't stick
But
around.
yeah, no, he might be listening on his phone in his car. I don't know. He's pretty tech savvy, so I wouldn't be surprised.
All right, I'll stop sharing.
All right. Yeah, thanks a lot for doing this. Let's keep in touch. I'm really excited about all of these things. I mean, this is fantastic. Like I said, this is log gamma is something that we were really excited about years ago, but we could, like, I don't know, we you know, things change, but I'd love to see that resurrected.
Yeah, I mean, I don't know. I liked, I mean, Jared seemed to get Although Jared's paper only kind of looked at these log linear models, but it really goes, it hits a lot of use cases.
Yeah, but did he release a package? I can't remember.
He didn't. I don't know why he didn't, because he has, I don't know. Do you know Jared? It's
Yeah, I do. And I know he was saying there was something about there was an issue with CRAN, but I don't know.
Yeah, no, yeah, I know they kicked his BCF. I mean, yeah, well, you know how CRAN is, I'm sure.
Yeah.
Yeah, I don't know why he didn't release it, or why it's not available, because I don't think there's any public packages that fit the Poisson. I mean, it's kind of weird. There are any that fit the negative binomial. That should be something that people have access to.
Yeah, it's a shame, but you're gonna fill that void very quickly, I think.
Yeah, hopefully. I need to, so that I can yeah, it makes yeah, it's something I've been meaning to do for a long time.
Okay, great. Well, I'll talk to you soon. Thanks for doing this. Hopefully the weather's nice down there.
Yeah, it's a little hot, but
Yeah.
all right, well, yeah, keep in touch.
All right, bye.
All right, bye.
All right, that's the is this thing on? Fell asleep. Can you guys hear me on this? All right, so that's the end of the workshop. Thanks for coming. Bye.